Namaste. I'd like to state my acknowledge this Nepalian Geotechnical Engineering Association Professor Ranjan. I was several times in Nepal here in 2016. I and Ranjan, one whole day session. I the chair and he was my co-chair at the Nepal Geological Congress. I did not go my background, but later on you can start. Because this is first the title, the Geotechnical Engineering and etc. etc. First I explained the water. Why you have water? Water everywhere. 50 years back, man can drink water without any hesitation from lake, river, stream, spring, everywhere. No problem. Day by day, it goes and it is now a commercial and number one patent healthcare item. This is not the daily life and healthcare. And the smart water now, this is smart water management and sustainable development. Sustainable development comes from the United Nations background, you know. And when water without management, it is a big problem. And I can say here, these things, everything, the society built in every country, we need to have great friendship, each country. I just, before go this lecture, I'm just introducing when one single basin contain one single country, no problem. When one basin, multi-country involved, then there is a conflict and etc. That is why I built the friendship and to look forward our society, the humankind, and healthcare, etc. Then you can go smoothing. Then bridging the groundwater, surface water dynamics aimed at climate change. Now the issue end product at the age last 20 years. The climate change issue is a bigger one. We are the geologists. I'm basically a geologist, then hydrogeologist, then environmental geologist, then engineering geologist, then disaster science, then climate change issues. Every country has some issues. In Nepal, I think this is great. In landslide, in Japan, the earthquake. In Italy, this is earthquake plus volcanic activities. At the United States and California, Alaska, everywhere the subsurface plate tectonics and movement, etc. That means that we are moving on the hot plate. If we can smooth using every item of the nature, then it reflects a good manner. Because time is important here, then I can go my lectures in four category. What is smart water and management, then sustainable development, then groundwater surface and dynamics and climate change issue I have already explained. And there is some figures for this lecture. Now I am one experimental form, the theoretical basis, then application, because it based on 50 years accumulation this lecture. My postdoctor, researcher, Dr. Johar Raja, he is assist these lectures with my suggestion. And I have already explained what is smart water and management. Then see four figures, but it is small here. I think I do not know the see. You can give already this Asian journal. You know, this is a journal. Then I'll go quick. The green water It classified the four grades, the green water, blue water, gray, and black. I already started the 50 years back, just a time scaling. Then blue water, it is two. When any hydrogeologist see the zone of saturation and zone of unsaturation, when zone of unsaturation, we call the soil moisture, then precipitation, the one element of hydrologic cycle, and plants transpire, evaporation and transpiration, both the soil and the plant. Total, including actually, if anybody estimate the water budget in each area, then he can estimate it, how much water we could use in the farming, health, supply water, etc., etc. And blue, that means groundwater. In Japan, I think here in Japan, the groundwater practices in Japan is restricted. I don't know this till now. Previously, when I was there, then the groundwater observation is restricted. There are only the surface water and lake water, etc. Gray water and then contaminated, Then this side is how to operate our resource potentiality into a smartness. And then if you can go the smart water, then you have to need instrument, interconnected, and intelligence. Now, the end product, the AI, and the remote sensing, the latest technology involved. Previously, we go dug well, then seawater. Now we're looking for fresh water by resistivity survey, geophysics, and general survey, geology, etc., etc. When you say, okay, this is the land of sediment, of sedimentary formation, then you can think about. When you go the hard rock, the igneous and metamorphic, then you have to think about why the storage is there. That is why interconnected, this is the society, and that is the latest technological system, and this is a figure of successive get way to direct the smartness and add up to the end. Then real-time pressure, these are the numerical mathematics. Here input the numerical mathematics. When you create the real monitoring asset condition for preventive maintenance, real pressure and water quality, everything instrument plus software programming. And then technological development, their phenomena, then we can control the whole system. And sustain is a simple one. If you can estimate the budget, when budget is surplus, okay, no problem. When budget is strange, then you have a problem. How to import your balance, and then you can go. That is why you have to maintain the sustainability, the resource potential. If you can 1 liter of water in Nepal, I think, is a cost rather than Bangladesh. And 1 liter in Europe, Germany, and other places. You know what? You can see the 1 liter beer, how much? And 1 liter drinking water, how much? And water can drink the first baby to end of the life. But you do not drink all the way on the alcohol and others. That is why one need water, That means that the raw things to input the update technology, then you output your healthcare materials. And this whole scenario, the process now. Now I go the sustainable, the SDG goal, that is popular now. The target, the universal and sanitation. Why here input the sanitation? In one time, some years back, in third world countries, the United UNICEF and others, they are putting hand towel and wash your hand and you latrine, the side by side. Then I complained to UNICEF, this is not correct, In the plain sedimentary basin, it is impossible. Then we took a project for ICDDRB, our Bangladesh center, to measure the contamination. Then we found this polythene. Then they stopped it. And now they are far distance from there. Because the pollutant also transported by the liquid water. Then concept, people, principle. I just, the importance yesterday, I think, in the women's program. The role of women in water, I emphasize on the women's because our coastal belt, when the hazardous conditions, cyclone, storm, high flooding, then we have the saline water input. There is no fresh water. Every woman is thinking about how to bring the water to his family. Same thing in the hilly area. If you go visit the hill range, there's no water. When you dig anything, then it's spring water, then maybe purchase. Everything is carrying, thinking, family is the women's. That is I emphasize here, the women's and economic value I have already mentioned, up to the table, how much cost these things. And in some way, I reported it is not easy for society to develop every corner to this type of water supply in the family life. And it nowadays, this is also estimated our poorest level, poverty line, water is one element, pure water. Here we set several steps. We can think later on and expanding this series. It is not, hello? It is not running. Next slide. Yeah, this, I have already mentioned this table. And then now this is, you think, now the latest technology, how to input the system, the real monitor. You have to some in front of you and then process and then clean water and then go the society and away. Next. Next slide. This is their system in nature. I've already stated the groundwater research and the underground aquifer. I think everybody knows the aquifer with the water-bearing formation in subsurface. And then surface water, then river water upstream, and from Himalayan water to up to the Bay of Bengal. It runs to India, Bangladesh, and others that goes, the three countries. And some rivers from Bhutan to go downstream in our country. And whole path is responsible to clean and maintain their resource. then our system and learn the young, the geologist or this community is learn the hydrological connectivity, topography, these things, everything I don't know, the topography, exchange regulator, temperature is one big element. And the climate change issue, all elements, temperature dependable, variable. When temperature increasing, nowadays, I've already last two days the conference, I hear summary, the temperature, rainfall some places, even our Bangladesh too, the shifting of the rainfall. But total estimation at the end, more or less equal. When you can go the time series, 100 years, then maybe some differences, but 1, 2, 3 years not, but they shifted. For example, in Dhaka city, within the 6 hours, 600 millimeter drop. Then the infrastructure go underwater, and we call the flash flood and wash out everything. But the 600 rain, precipitation, so-called, in Europe or even in Germany, the average, this is 5 to 600. In Bangladesh, this is sample, more than 5,000 millimeter per annum. It depends on locality. Then you think about the vertical precipitation, upstream forcing, how terrible in downstream Bangladesh. And we have a disaster, we say, when I visit in Saga in southern Japan, there is a lowland technology institute, one lowland technology institute in Netherlands, one is in Canada. But the land reclaim, the system, the society developed, they think about how much we can make for poor peoples this way. Next, please. Next slide. Next, this is again. Oh, the integration strategy. This is now the software program. Tools, the software, the MartFlow. I use this MartFlow program since 1986, when the starting, the MartFlow Colorado State University, to USGS, to Berlin, and my field experiment in Bangladesh. You know, the terrible, limited program, the 2-dimensional mock method of characteristic, and this is MartFlow 3-dimensional, only the flow direction, not contamination at that time. At that time, limitation at 36 by 36 grid and 18 by 18 grid. That's it. Then terrible history of the modeling, first time to land. The interaction between water, groundwater, integrated. Everything I first explained the technology development upgrade. This is not easy. Previously it is easy because man cannot find or know about the contamination, etc. And their healthcare is good enough to resist their health. Now, everything, your health, your body is a laboratory, you know. You don't everything consume. Sometimes it's overheating, then problem. This is the honey. Our time is. Next. Now, climate change. Here you see there's some figures I stated here. Global warming. What is global warming? The shifted precipitation I've already stated. Melting ice, and geologists know the age of the earth. 100 years is not a matter, you know, which goes timely. When this 100 into 1 year, then it is problem. Then think about how the induced force here in the nature, and that nature is jeopardize our society. Then we think about, okay, we can make a disaster science, a disaster management, preparedness, etc., etc. This is broken. And the water is damaged, then water can be captured by our controlling, etc. Next. Next slide. And then reduce snow peak. This is some one modeling nature. You know, you can see the decline groundwater. When the groundwater decline, then in the coastal belt you have the problems. First, salinity invasion, then subsidence in the salt subsediment. And increased hydrological variability. This everything is your repairing your material, the resource. Resource is water. So you have to all the time regulatory. Okay, because professor always moving, you know, that is why this is not fixed one. Thank you. And next. Now I state here a simple, you know, the last finish, the COP 30. Now I state here the 16, 21, 27, 28, 29, and 13, what is the target? Because this is our conference here, 3 days in Kathmandu. We are here, we are coming from different sources, different university, company, others, ministry. Everything, after finishing this conference, then we can make one Kathmandu Dhaka framework, you know, declaration. This is the so. After 2 years later, then we go. If anybody survive, then we go to Japan, there's Osaka, etc. Then again talking. But talking, but planning problem. Funding problem. These things inside third world country. I'm supporting with this. Only the 20 countries input the whole things. But we can mix up whole things, at least a minimum level of society, then I think everything is okay, smoothing. Next, please. And this is COP 30, thematic area, and global climate action agenda. You know, the ICCP, when it developed, then I was in Hamburg in 2011. There is a conference, this climate change issue. The first founder, president, he's there. He's from India. And then we think about the discussion about this matter. Now this transfer nowadays is a COP. And this is now behind the climate change action agenda, adaptation. Now this last two, climate financing, now this or disaster financing, and justice and inclusion. Justice, I explained already, the friendship. Friendship means when you're good friendship, then justice you have, automatic. But with some conflict, then it too. In one country, by individual district to district conflict with the water, you know, upstream and lower stream. But no sharing, no budgeting. You have to estimate it total area budget, then you can contribute and distribute all the resources. Thank you. Next. And you can survive this 4 figure here. Climate, now the term, the resilient wash solution. I've already explained before the UNICEF program, the tubewell and latrine. And now in our third world countries push the wash program. This is another phenomena. Okay, next, health, fish. If quality is okay, then everything is running. Then water management is a core pillar. Now, here climate action, and here is the national NDC, the individual countries planning and guideline. And adaptation plan, community. Okay, next. A water-related target, climate adaptation indicator, real-world outcome measurement, and next. This is, I have already, this is a fund, local community, water risk management. Next. You see the female leadership. So, next. This is the outcome of this next COP. Water sustainability, community adaptation practice. Ultimately, we go to society develop, the resource. Next. This is individual sector. They are subsection to, because you have to estimate the budget, then you have to do to finance, then you have to target the section-wise, then accumulate total volume of the budget. Next. This is ecosystem, system to eco. Then these terms are terminology incorporated to develop the initial condition to up level. Next. Next. I've already explained these things in Bangladesh. Next. Now the Bangladesh last your session, somebody raised this guideline, the Indian geological guideline. This is, the Bangladesh national plan, then water rules, decision, here up to date, the Delta plan, the 21. This is update in Bangladesh. Next slide, please. This is, I think, in Nepal policy and law. I stated here. I do not know the Professor Ranjan. This is okay. You're in Nepal. You can check. I have collected from your website. Older. Okay, then you can put here new one. Next. This is my new concept, anthrotectonic cone of depression. When I arrived in Nepal this time, or Bangladesh is severe under earthquake system. In 1 week, there are the 5 or 6 times, Professor Obaidullah is here, 6 times this is earthquake. Then we can think about these things. This is a natural cone of depression, hydrogeological background. Now I am impact with the tectonics and 3 material interaction. If any places, then any catastrophic may be out place. Next. This is cone of depression behind a decline and turbulent and low profile. Next. Again in township, I don't know. Then Kathmandu water at that time in 16. This is some places cone, some places in Kathmandu airport nearby. There's some sinkhole and others. Here is a limestone barrier in this Nepal geology. And in Bangladesh is the sediment and the subsidence. This is the difference between the lithological background. Next. Now, formulate this is two senses geology input. Fault and structural geology, then earthquake, subsidence, tectonic setting, crustal deformation, and this pathway, and then we can go this way for development, our future generation focusing. Next. Dead Sea fault, this is some example. Next. Yeah, this everything is a technology update, then policy, manage, and then auto. Now the water with current, you know, this currency, local currency to input, and then you bring water in some places. Next. This is a systematic whole things, the conclusion. Conclusion means in one single sentence, this you have to maintain good environment, then you retain from resource. Next. Okay, thank you so much. And I think I have some time, then I think open discussion, some, if possible, if permit your committee. So I'm here, if anybody questions.
Yeah, so thank you very much for this interesting presentation. The time is over, so unfortunately we don't have the time for questions, but I think that we can, if someone has some question, we can use the time during the tea and coffee break to discuss about several interesting topics that you introduced during.
Then I thank you, your planner, and here they're working some things, everything. I acknowledge it in a good way to complete our conference here. And next part, I think in Dhaka, no? Yeah. Okay. I have already booked by Sakwa.
Okay. So. Thank you very much again. I think we can move to the next presentation done by Professor Shahid Azam. Professor Shahid Azam is a professor of the Environmental System Engineering at the University of Regina, Canada. And the presentation is New Methods for Characterizing and Modeling the Engineered Behavior of Expansive Soils. Thank you very much. Just check if the remote control is working. Okay. Okay, thank you very much.
I'll follow my own timer. Just check. Thank you very much. I'm going to switch gears from water to soil. And what I want to discuss today is a branch of physics, which is soil mechanics, and apply the principles of soil mechanics to a unique type of soil, and thereby developing how we can actually make new science, therefore making design for infrastructure better with this class of materials. So my title is New Methods for Characterizing and Modeling the Engineering Behavior of Expansive Soils. I must acknowledge my co-authors, Maki Ito. This was her postdoctoral work, but you will see she stayed with me for almost 15 years for master's, PhD, postdoctoral 1, and postdoctoral 2. And then in the city of Regina, and I will tell you where Regina is shortly, we have a world-class engineer, Wayne Clifton, who's the president of Clifton Associates, providing funds and know-how, and also um, converting those ideas that we generate at the university into actual practice. So our third co-author is Wayne Clifton. Before all of that, I must really thank the organizing committee, and especially Dr. Dahal and Dr. Sakhawat and others, for giving me the opportunity to come here all the way from Canada to Kathmandu as a keynote. Thank you so much for that. And also my co-authors. I'm at the University of Regina in Canada, and I will tell you where that is shortly. This class of materials is not unique in Canada. This global map is telling us where expansive soils exist across the world, basically. And they exist in Canada for sure, and in South America, parts of China, India, and Australia, and South America. And if you superimpose the global climate map on this map, you will realize that these locations really coincide quite well with semi-arid and arid zones, which means that the water, the soil will almost always be unsaturated, that is, the pores will not be filled with water unless it rains on it. And therefore, the whole game of expansive soil is the presence or absence of water. Let's look at two soils. On the left, I have a sandy soil, and I saturate that soil. On the other side, I have an expansive soil. When it sees water, it expands. That is, it changes in volume. Okay? So it looks very simple, but the question then becomes why this type of soil expands. And the answer is in the mineralogy of the problem. It's not like sandy type material, which is mostly inert in nature. This class of material, such as schmectite, elite, or chlorite, these are 2-to-1 clay minerals with large specific surface areas and net negative charges associated on those clay surfaces. They're generally silicate ilmenite type materials. The difference between schmectite and elite would be the presence of that potassium layer, which is actually, potassium is positive, so it is trying to make that negative charges basically satisfied. And in the process, the basic building block is closer to the next building block. In the case of chlorite, there is basically no charge deficit available anymore. If I look at schmectite, just under dry conditions, there is 9.6 angstrom of space available that can be filled by water molecule. Under wet conditions, therefore, the water, being bipolar in nature, will arrange itself in such a way that it fills that gap and therefore pushes the clay particle away from the other clay particle. This is the reason for swelling, or at least the theoretical reason for swelling of clay, and reaching basically 14 angstroms or so, which is almost 1/3 of its original volume. That is the swelling part, and when the sun is active and it does its job, that is, evaporation is now taking place, that water is removed and we see shrinkage. So now you can appreciate that swelling and shrinkage is a transient phenomena. Okay? It depends on how much water is present or available or it's gone. In a soil profile, therefore, the top, let's say 3 to maybe 5 meters in Regina, it's 3 meters or so above the groundwater table, that is, all soils are unsaturated. We are living in a semi-arid zone, and therefore, above the groundwater table, there is a net negative pore water pressure. Now, the soil generally remains at the plastic limit, and plastic limit is about the water content at which the soil just tries to crumble if you try to make a roll out of it, okay? So in that case, when the clouds come and when it rains and so on, or when there is that initial, let's say, freezing is done and then the meltwater is coming, then the soil can swell. Most of the time, the soil will be unsaturated and therefore it will be in the shrinking mode and you will see surface cracking and so on. The reverse is then true also in relation to evapotranspiration and so on. But all of my buried infrastructure and also roads, which is just at the surface, and maybe walkways and so on, natural gas pipelines, water supply pipelines are within the unsaturated zone. Therefore, when it swells, these go up. When it shrinks, they go down. And cyclic movement of these over year after year after year makes the infrastructure break and fail. Okay? So I'm going to show you some photographs to confirm with you that that is actually the case. But here what I want to also mention that you're seeing that, let's say, a yellow line, which is the hydrostatic line, below the ground surface and reaching a 0 value at the groundwater table. When it is really desiccated or dry conditions, you are following the blue line, which is the soil has a net water deficit. It is in suction mode. Suction is the difference between air pressure and pore water pressure, and we are considering the soil pores as a continuum with the climate, with the atmosphere, and therefore the green line. When it rains, okay, the water, the air pressure will become 0 at the surface, but it gradually goes down and eventually reach the hydrostatic line. So therefore, swelling and shrinkage is a function of suction. Suction is derived from what is happening in the atmosphere and the response of the soil to what is happening in the atmosphere. Does that make some sense? Okay. If we are on the same page with respect to that, then you can appreciate why do we have all sorts of trouble in areas where there are expansive soils. I'm showing pipeline failure in the city of Regina. We have 1,200 kilometers of asbestos water mains. Each break is costing us $50,000 to repair. And we are seeing an increasing number of pipe failure breakage in the city. It's exponentially increasing, reaching now almost about 40 breaks per year. That is $2 million per year, just for pipe breaks. I'm showing pavements are cracking, especially in the older areas. If you are restricting that movement of the soil, right, then it will crack. If you allow the soil to move up, you're seeing domes on the surface. So if you come to Regina, you will really see wavy roads. And that is surface heaving. And we are also seeing lots of issues with meters. And in this case, I'm showing in the gas pipelines and the meters associated with that. This meter is fixed to the boundary wall of the facility, right? And ideally, it should be at an angle of 45 with the horizontal, that connection. But when it moves up, that angle is different, and when it moves down, angle is different. And so it's that cyclic movement up and down. Water was easy because you can follow it. Gas is not easy because you don't know what is leaking. We have seen houses burnt in the area, right, because of gas leakage and so on, and therefore it becomes a problem. Okay. So where are we? With this context, I just want to maybe present to you that green area is Canada, and we are somewhere in the middle of the Canadian prairies. And prairies are vast areas with no mountain for thousands of kilometers in all directions. It's plain, okay? In that plain, there is that glacial movement or glacial advances, 7 of them, back and forth from the Hudson Bay all the way to California, right? And eventually, in the last about 7,000 years ago, the last glaciers basically retreated and so on. So we are living in a glacial lake-type environment. First, I'm showing the boundaries, which is the purple line here, of the city of Regina. That's expansive clay. This clay was deposited. It's a volcanic ash. The presence of sodium, chloride, calcium, potassium ions coming basically from a previous marine environment and semi-arid climatic condition resulted in the formation of expansive clays at this location. These are very common across the prairies in Edmonton, in Winnipeg, and so on, and they have different depths. In Regina, we have the expansive clays at the surface, okay? And that's why we are seeing a lot more issues with this kind of material. Okay, I'm showing here the section of the soil, and you're seeing 2 types of cracks in this original material. This is not compacted, this is not a slurry, this is a soil geologically given to us through the Quaternary. You're seeing 2 types. At the surface, there is alligator type of cracks. Associated also with them is the white color. That's the salt precipitation and so on, okay? If you just remove that kind of layer from it, you're seeing more hairline cracks, vertical, and that is because this whole area was covered with up to 1 kilometer high ice sheet. When you remove that, the load is gone and the soil retreats, it's more volume, and therefore it has cracks. All over consolidated soils will show fissures. Also shown in the table is the presence of high amounts of smectite and illite in the soil, and also the pore water is showing us relatively not super high, but good amount of salts within the pore water. Okay, couple that with my climate. Here I'm showing 2 indicators of the atmosphere. The mean temperature in the city is 2.8 degrees Celsius annual temperature, but that is meaningless given the range of temperature, which is somewhere around the 35-degree range, -20 to +15, okay? The precipitation is low, not in the hundreds, not in the thousands, it's 384 millimeters per year. And most of that is also within that summer time, or spring-summer time. So it is this zone of time in which I'm seeing a lot more swelling and shrinkage every year, somewhere around the April to October time frame. And I'm after that, right, to actually develop some kind of method to understand that. So far we learned that swelling and shrinkage is coupled with the water flux, the presence or absence of water in the surface layer. And that comes most of the time from the environment, from the atmosphere. Is it raining or is it evaporating? Second, we learned that this is a cyclic movement. Third, we learned that it is a transient movement. It changes with time. And also, we know that it is a function of the soil fabric containing those fissures. It's not a slurry, it's not a compacted soil, it's as is natural soil. Okay, so now we know that. The question then is, are we ready? Should the conventional methods be enough to give us some idea about how to design infrastructure? We use the classical odometer test, one-dimensional, right, to determine deformation. Usually we get a final number, which is a settlement number, and then we base all of the infrastructure and buildings and so on that. But that's not enough. We saw that that number cannot capture cyclic, transient, fabric, all of the above. Therefore, we now need to develop a new soil mechanics that can capture these unique features of unsaturated, expansive soils. Here is the classical Terzaghi theory, okay, which is basically derived or using the heat equation. The rate of change of pore pressure is equal to the second derivative of the pore pressure with respect to the depth. So the change in slope with respect to the depth, and he used a coefficient of consolidation, which is a constant number. He said the soil is so small, hydraulic conductivity is about the same, the gamma of water is known, the initial conditions of void ratio are known. I will give you a small little coefficient of consolidation that you can determine from the consolidation test. Now that's good. That's not enough. We are here presenting a new method, which is suction-based. Remember, suction is transient and all of those things, and it is very similar to loading. We all know loading because of geology, right? But suction is more important for that top layer of soil, which is affected by the atmosphere. So therefore, let's look at this. Now I'm presenting very, very similar way. The coefficient of consolidation, we are now calling it the coefficient of swell shrink. Okay, everything is the same except for two things. The hydraulic conductivity is now a function of suction, and the coefficient of volume change now is a coefficient that is also dependent on the derivative of a certain equation. I'll show you how. He said, my coefficient, that's a number. For us, it's not a number, it's a function. It's a function of suction. And you can see it's a derivative of the void ratio with respect to suction. So I'll do those. And then obviously, the hydraulic conductivity is not a number anymore, it's a function. All those functions, right? So what is suction? We know about suction. We have made our what is it called? The sand castle, and we have already seen insects can actually sit, if you will, on water or sometime on that. And that is because there is that pulling of the stresses on each of the droplet. If it is somewhere in the middle of the water bowl, it will be equal in all directions. But when it sees that surface, it's not equal in all directions. It stretches it. There is no opposite movement, and therefore the resultant is suction. If we understand that, we have already done this experiment perhaps in grade 10 or before, where we took those different sizes of tubes and we determined the capillary tension through this. That is, in essence, what we call suction. Okay, so I now want to maybe present a small little set of figures, some of which we know and others we will try to know. First one is the classical consolidation test. in saturated soil mechanics, that's the first thing they teach us, right? Which is a load deformation type, void ratio, or the volume will change, and if you apply loading on it, that's how all these structures are made. Okay. We know two more curves. One is the soil water characteristic curve on the left side, and the other one is the hydraulic conductivity curve. Those are curves now. Previously, Terzaghi said these are numbers, but not one number only. They are functions of suction, okay? And then, so we know that from unsaturated soil mechanics, right? Blight and others, and Bishop and so on, they told us about these two plots. That works well if the soil doesn't swell. But the soil, in this case, does swell. So we have to add another plot. In this case, it's a shrinkage plot with void ratio on the y-axis and water content on the x-axis, and it's an S-shaped curve. When we develop that interaction between unsaturated soil mechanics and the shrinkage curve, we can now develop a new mechanics for expansive clays. And that's what we have been actually trying to tell people. So Ito, in this case, she got so much data from previous work. I'm just showing a blue line and all natural soils. Blue is slurry and other soils are, okay, so you can see two groups. This is the water content versus soil suction. This is the shrinkage, which is again, blue is different from soils. Blue is slurry and other are soils. And we can fit the Van Genuchten fit to it, right? Which we know about quite well. And I also know consolidation test, classical for this type of material. We compiled all those data. And now, from those data, we can determine also the hydraulic conductivity using the Taylor's method, or we can directly measure the hydraulic conductivity. And basically, hydraulic conductivity is now not a number, it's a function of suction, and suction is related to the saturation and so on. When I use all of that information, I can now convert that into one type of curve. On the x-axis is all normalized void ratio, be it from consolidation curve or the swell shrink curve or any, and on the y-axis is either applied load or soil suction. Again, blue line and soils, okay? And I can fit through these data, and I find that it's very similar to the Van Genuchten equation. It's a sigmoidal equation. When I know that, now I can convert all of that information to swell shrink coefficient, which I promised earlier, okay? Swell shrink coefficient is what? The hydraulic conductivity is variable, and so is the derivative of the E-based shrinkage curve, water retention curve. So now everything is changing, okay? So I'll use this coefficient now and couple that with the atmospheric parameters causing precipitation or evaporation. And the top one is showing precipitation for a 10-year time frame. And then we have temperature, solar radiation, relative humidity, and wind speed, and so on. All of those will result in evaporation. So water going out, water going in to the soil and causing either swelling or shrinkage. So now I can determine suction over the entire period. The black is showing exposed surface of the ground, and I can cover it perhaps with pavement such as a road and whatnot, or a walkway, and I can see the red line. I'll use that suction value, okay, to predict ground monitoring actual data over a 10-year time frame, and with depth you can see there is a lot of scatter at the top, but that scatter reduces with depth, and at about 3.1 meter, the load of the soil is enough to cancel any deformation of swell and shrink. And that means that all pipelines buried in or roadways or walkways will be affected by the swell shrink. It confirms that. And so if we have a paved surface, it's even better because the water ingress or going out is kind of controlled. There is discrepancies which we attributed to the assumptions within our method, within the material property determination, and so on. There are always experimental and monitoring data errors and so on, but we are really confident that based on the Terzaghi theory that everybody uses, our theory is very similar. You just need to determine three things: water retention curve, hydraulic conductivity, and swell shrink curve. And you can use the remainder of the Terzaghi method. So, my summary. The approach is based on the analogy that the swell shrink coefficient is the same as the coefficient of consolidation, and it can be determined from these three curves. The governing equation is similar to the Terzaghi classical equation, so we can easily use it, and we are familiar with that. The model comprises two components: the soil properties and the climatic conditions, and it adequately captures seasonal variations, right, of precipitation and evaporation, and it is useful not only for initial design, but also for the performance prediction, cyclic and transient conditions. Here is a couple of references that we utilized, and we also used them in the publication. I would like to thank the University of Regina, our funding agencies, Clifton Engineering, and so on. And I want to thank again all of you for listening to us patiently, and ARC 15 for inviting me, and above all, the Mother Society of IAEG. Thank you very much.
So thank you very much, Professor Azam, for your interesting presentation. Again, I think that during the tea and coffee break, there will be the possibility to discuss more on this topic. And then I would like, it's a great pleasure to introduce Professor Giovanna Vesia, my colleague and friends of the Italian IAEG National Group. Professor Vesia is a professor of engineering and geology at the University of Chieti Pescara in Italy. And the presentation is Neo-Deterministic Seismic Hazard Approach for Seismic Response Analysis in Urban Areas, a case studies from Italian territory. Thank you.
Thank you, Mr. Chairman. Good morning to all the audience. So, moving from the, okay. So, moving from the scale of the sample to the scale of the real life, the real volume of our urban areas, I would like to discuss it, to introduce my topic of this morning, that is the prediction of local seismic response. But what is that? I mean, we have under our eyes worldwide what happened after strong earthquakes in our urban areas. I don't know if some of you, but in Italy, for example, we started from 1980s to record and to study the local effects that, of course, caused many loss of money and many victims. So, how to do? This is the point. So the local seismic response is a complex field of research because it involves many expertise and many field of knowledge. It can start from the source mechanism of the seismic, the rupture at the fault and the propagation of seismic waves. Then, at the site, when these body waves, P and S waves, arrive to the site, they experience a changing in amplification, in frequency content, and in their duration due to many effects that I try to report on the right side. I mean, the contrast between the rigidity, the stiffness of rocky formations and the softness of local deposits, quaternary deposits, soils, generally speaking. But it is an effect that can be catched by 1D numerical analysis, but it is not the only one, because we can see in the basin effect that when the shape of the rocky bedrock is convex or concave, it changes the response of these seismic waves at nearby the surface, generating amplification and, of course, damages. These amplifications are moved from some range of periods or frequency to the others, and this can be, it can affect infrastructures and buildings that are the next and the most sensible structures on the surface. The amplification can are not only the effect at the site, but the instability can be induced. This instability involves liquefaction and slope induced instability. So we need to manage this complex phenomenon that has been studied since 15 years in the 80s years, both experimentally and numerically, assuming a decoupled approach that is defining the reference seismic hazard at the national and regional scale, and using these results as the input motion for local site seismic response analysis, defining, so in this way, the site seismic hazard. In the last 20 years, improving the numerical resources, 2D and 3D simulations have been developing, and many other methods to have an all-in-one tool to assess the response seismic prediction came through. And now the physics-based numerical simulations are now used. They have some advantages. They show some advantages. The first is they simulate in a more realistic way the phenomenon that is complex and involves different analysis during the path from the source, the rupture, to the site. And it involves modeling also the seismic wave propagation, but by taking into account the tensor nature of the earthquake ground motion and the causality of the P and S wave propagation in the lithosphere. So among these new methods, the neo-deterministic seismic hazard assessment try to solve this problem. I mean, try to manage this prediction of the local seismic response by means of an all-in-one approach, moving from the scale of the national and the regional scale to the local scale. So the content of my presentation will show some features of this method that has been developed during the last 20 years. And in order to show the potential and the capacity of this method to predict at the site and to show the effect of the propagation of these waves at the site, I will show a case study in Kyrgyzstan. Of course, validation has been done on this method at the regional and local scale. Then results will be presented and some concluding remarks will be drawn. So, the all-in-one method, neo-deterministic seismic hazard assessment, can be considered to be divided into 3 steps. So the first is the source characterization, the second, the wave propagation, and the numerical analysis at the site. So for the seismic sources identification is correspond to the first step. But for this point, 2 different methods can be used according to the available knowledge of the seismogenic zones in different in different areas of the planet. So if we have, for example, in Italy, we have a seismic catalog and seismogenic zonation called ZS9. And so we can use in Italy this type of seismogenic zonation to characterize the seismic sources, but together with the possibility is to use another method that is called the method of the seismogenic zones, nodes, that implements the pattern recognition based on the morphostructural analysis that, of course, must be done according to different tectonic characters and regimes of different parts of the planet. Then, starting from one of the other method, we can use the earthquake distribution by discretizing the area into cells of 200 kilometer side, and then smoothing the information, considering the variability, the uncertainties of the main parameters at the source. So, starting from this earthquake distribution, we can represent the focal mechanism that are taken for each seismogenic zone, and we can select the controlling earthquake, considering the maximum one between the 2 methods mentioned before. In this method, the maximum magnitude is estimated as I previously told. But the magnitude used is not the maximum, but the designed magnitude, which is, according to Panza-Rugarli law, which is represented by the maximum, the controlling earthquake, plus a factor of safety, taking into account the standard deviation of the magnitude estimation at the site and in the region, regarding, of course, the source, the seismogenic source, and a coefficient factor of safety, which varies from 1.5 to 2.8. According to the neo-deterministic seismic hazard method validation, this coefficient, so the production between gamma and sigma, works to be as 0.7. Then the synthetic seismogram are computed by this web app named Xeris. It is open. Of course, you need to know how to implement data into this web app. But the seismograms are computed based on the structural model and the seismic sources of the controlling earthquakes. This approach doesn't use the ground motion prediction equation. It considers the tensor product of the earthquake source functions and the Green's functions of the inelastic media by which the seismic waves are transmitted. Regarding the lithosphere mechanical properties, 5 parameters are taken into account that are the rock density, the two velocity of the P and S waves, and the quality factors respectively. These properties are assigned leveraging a structural cell model of 100 kilometer size and according to seismotectonic parameterization that in the Italian peninsula was conducted by Brandmeier et al. In 2010. So, the fault rupture simulation is again another property, another step of this only one method, and it, of course, from this fault rupture simulation, we have to derive the mechanism of the rupture. We have to consider the magnitude of the source, the simulation of the kinematic source rupture process is then performed by pulsing code, which consider both bilateral and unilateral sources for simulating this rupture. Of course, taking into account, as I told you before, the uncertainty of the property of this fault rupture simulation, the Monte Carlo simulation was considered so that in order to produce 100 or more realization of these synthetic accelerograms due to the fault rupture simulation. Then the seismic wave propagation starts from the source and arrives to the surface of the site under study. How it is done by a hybrid method. So to propagate the seismic waves in far field, the model summation technique is used. Then in near field, the ground motion is calculated by the discrete wave number technique. That means that at the bottom boundary of our site model, the generated causal wave field is injected into the heterogeneous area using a finite difference scheme. Then, at the site, we have to understand what's happening. And we can do that by calculating design, if we are interested in retrofitting or building structures against earthquakes, or through microzonation parameters that are needed when the urban planning try to derive hazard maps. So the results can be expressed in terms of a statistical distribution of synthetic seismograms and response spectra, both calculated at the surface, at the bedrock, and at the bedrock. The resulting response spectra is called most credible spectral response because the spectra, of course, at the site we have 100 spectra due to the 100 realization of the Monte Carlo simulation. But these spectra are fused according to different seismic sources in a mean spectrum, which is called most credible spectral response. I'll show you in a moment. The other information we can have, which is quite interesting and quite new, is the wave field in terms of acceleration, velocity, and displacement at the site in the model, in the difference element model, where we can even represent in the time the acceleration, velocity, and displacement the seismogram at control point that are user defined. Here we can see in the figure we can see I selected 6 points on the section, the 2D section that I will discuss in a moment. Finally, the amplification functions can be calculated. It is a function, so it is defined in the frequency domain, and it represents the ratio between the response spectra on the surface of the 2D model. At this moment, the neo-deterministic seismic hazard assessment is developed for 2D analysis, but 3D is coming. Anyway, so in this case, the amplification function is the ratio between the 2D model, the response spectra of on the surface, and the response spectra on the outcropping bedrock of the 2D model. So we can see that both these results are calculated at the surface according to the common method used in the decoupled approach. A very important step in this, in the neo-deterministic method is the validation strategy. So, of course, these strategies must change according to the scale considered. So, in the case of regional scale, two pilot areas are considered, and they are Italy, of course, and the southern margin of the Tibetan plateau, that is the Sichuan and Hunan provinces. So in this case, we, of course, defined and used information about and knowledge about moments, but we, so in these graphs, we put on the X line, on the x-axis, the PGA estimated by the neo-deterministic method, and on the ordinate, the PGA measured at by the seismic station. And we noticed that in the Italian case, the moment design, the magnitude design, so that is calculated according to the Pansa-Rugarli law, interpret the 92% of the data, of the measured data. Instead, in the area of the Tibetan plateau, 100%. It means that the neo-deterministic method is able to predict the value, the ground motion value of the acceleration by using the maximum moment plus 0.7 coefficient of for design. Instead, the validation strategy at the Chieti site or at other site is based on the records of the strong motion at seismic station. So in this case, in this case study, we used the seismic station in yellow, and we considered the resultant of the combination of the two horizontal components of the main shock of the 6th April 2009 L'Aquila earthquake. And in the graph on the left, you can see that the red line is the mean estimation among the 100 realizations of the seismic response, the spectral acceleration at the site, and the black one is the signal measured at the Chieti seismic station. Although the mean value of the red line estimated by the neo-deterministic method catch the trend of the signal at the site, the main important point, in my point of view, is that the 100 realization are able to represent the waving trend of the signal, of the real signal that is affected even by the local conditions, is able to envelope this trend by only one sigma, one standard deviation. So we consider this evidence a validation at local scale. So the case study of Chieti city area is in here. The city is divided, can be divided into two portions. The hill, the Chieti hill, is settled on 330-meter relief, and with the Pescara River Valley on its western bank. And the second part is the newest contemporary town and the business district, and it is settled in the alluvial plain of the Pescara River Valley. So Chieti falls in the seismic zone 918, according to the seismic zonation of the Italian peninsula. His seismicity is moderate, and the hypocenter depth varies from 12 to 20 kilometers. The main faults that affect Chieti are the individual ones here in the left graph, and one composite in the right graph, in the right figure, that are all considered in this study. So in these tables, I reported the main characters at the source of these, of course, of these faults that were used for simulating the seismic rupture. Then a few words on the geolithological features of Chieti city. It is made up of sub-horizontal layers of the Mutignano Formation, which can be considered its regional geologic bedrock, but over them there are alluvial and alluvial colluvial deposits, which are can be considered soft soils. As you can see, I put here the values, the 5 parameters we used in the neo-deterministic method to simulate the dynamic response of these viscoelastic soils. And, sorry, the section, the 2D section considered is A first, and its length is about 5 kilometers. So this is how the number of the information, mechanical and geological information we use to reconstruct this section, but it is a common way of working. And then the lithospheric parameters are reported in here, and elements of the numerical model used in this analysis. Then results. So at first, we can see the wave field at the site. And of course, the input motion has an inclination, a direction that is caused by its propagation from the source. So it is not forced to be vertical. We can have 3 components, the 2 horizontal, radial and transversal, and the vertical one. And we can see here that thick soft deposits of about 30 meters that are on the plain area of the section causes the highest amplifications compared to the relief. This relief is not that steep, but it could be, at the very beginning, it could be considered to work a pivotal role. It is not, but on its flank, some amplifications where the soft sediments are placed can be recognized. Then the response spectra. These response spectra are very important for the building, retrofitting, and construction. These ones are not are reported according to the most relevant, most affecting seismic sources at this site. You can see in the table the number, the colors correspond to a number, and this number corresponds to the different faults. The first one, the nearest one, is the composite that, of course, as we can see in the P2, which is the most amplified point, and over the thick soft deposits, we can see that the response spectra, the design response spectra, is made up of different portions coming from different response spectra caused and generated by different seismic sources. So the design response spectrum will be the envelope of all these portions. For example, yes, just a few minutes. Under the 0.5 second, the composite source is relevant and cause a large amplification, while between 0.5 second and 1 second, the Tocco-da-Casauria individual source is prevalent. Then we can see the amplification functions here on the axis, on the horizontal axis. We have the space, which is, as you can see on the bottom, is the point of the section, while on the ordinate you can see the frequency. So we can have the response at the site in terms of these the most amplified frequency that are very important for structural, for avoiding the double resonance with our structures, all over the section. This is another, sorry. This is another example because we have all these results coming from all the sources we considered. And then, final remarks about the capability of this new method to all-in-one method to simulate the seismic rupture, from the seismic rupture to the seismic response analysis. Of course, the advantages is to have a more realistic representation, considering the real direction, the incoming direction of the seismic waves, and take into account the geomorphological characteristics of the site. Some limitation that in some cases we are overcoming is the 2D analysis that will be 3D in near future. Of course, we disregard the seismic wave reflection to the heterogeneity, due to the heterogeneity of lithospheric rocks, but it is, okay, it is a limitation. And another point that we are trying to overcome is considering only viscoelastic behavior instead of equivalent linear behavior. But even in this case, it is to come. So, of course, as I told you before, this method promotes the resilience in urban areas by not only providing response seismic design analysis, but also microzonation mapping. Thank you so much for your attention.
Thank you very much, Joanna, for your great presentation. And we move to the last one, okay, made by Professor Tumai Kadaki Koka. Professor Koka is Associate Professor at the Muğla Stiki Kokman University in Turkey, teaching engineering, geology, rock mechanics, and slope stability and landslides. And the topic of the presentation is erosion and mass vesting process in post-wildfire mountainous terrain, impact and challenges. Thank you very much.
Thank you very much. Sorry. Hello and namaste, everyone. It's a great pleasure to be here at the 15th Asian Regional Conference of IAEG in Kathmandu. Kathmandu is a truly authentic and spiritual city, and I would like to thank the organizers for their great efforts in making this conference as a success. And I'm Tumay Kadakçı from Muğla Sıtkı Koçman University in Turkey, and I'm also serving IAEG as one of the committee members of Young Engineering Geologists Group. And this is my 15th year in engineering geology. And I've been studying post-wildfire slope stability since the devastating wildfires hit my hometown in 2021. And the previous presentations in the conference pointed out that climate change spikes the rainfall amount and intensity, and eventually the number and sizes of landslides increase. And wildfires make the slopes even more susceptible to those changes and compound the effect of rainfall. So today I would like to share some insights into how wildfires affect the rock and soil slope stability, as well as challenges and some future implications. First, we will discuss why post-fire terrain stability matters. Then we will move through processes, challenges, and future research directions before ending with thoughts on policy, resilience, and collaborative work. Yeah, wildfires are becoming increasingly frequent and severe across the world, and they are posing a risk, especially if they occur in close areas to urban lands. So the burned area and the number of fires graph, as you see on the left, taken from the report of International Association of Fire and Rescue Services, show that the Mediterranean basin and Western North America and parts of Australia and Asia have seen record-breaking fire seasons in the last 5 years. And in the same report, it's documented that human-caused fires were far more frequent than the lightning-caused ones. So, while the climate change is certainly a driver, human activities remain a significant contributor, including land abandonment and unplanned urbanization. After that, lightning and electric leakage along the electricity lines are the second major causes of wildfires. On the right-hand side, you see the organizations or associations that are contributing both at the scientific and social and policy-making levels. So what makes wildfire studies so challenging is that they are not standalone hazards, but they initiate the chains of hazards. So once the vegetation burns, the story doesn't end. The geohazard chain, illustrated by the figure on the left, started with the wildfire driven by global changes such as climate change and expanded urbanization and so on. Immediately after the fire, the produced ash dramatically decreases the soil's permeability. Water repellent or hydrophobic layers often formed close to the surface of the soil, leading to increased runoff in the first rainy season after the fire. On the other hand, root strength is lost, and soil shear strength is reduced due to burning, which in turn results in overall loss of soil strength. And in some cases, the erosion rates are up to 500 times more than the pre-fire levels. So it's a very significant increase. The transported material by erosional processes can evolve into debris flows and then shallow slides because the transported material is loose and unconsolidated, so it becomes more sensitive to gravitational forces and also water saturation. At the same time, fire accelerates exfoliation and cracking in the rock mass, and this process can continue for more than a decade. So as a result, rock falls may occur in steep terrains. With the ongoing erosion and shallow sliding, the soil layer in the upper slope becomes thin, and which further slows down the recovery from the fire. For example, Ringers et al. Showed that debris flow activity right after the fire can persist for up to 3 years, and in the wildfires occurred in Southern California. And they reported that this debris flow activity evolved into shallow slides after 3 years. So, of course, triggers such as rainfalls still play a significant role, while the post-fire terrain will be more vulnerable to these triggers than it was before. And our study in southwestern Turkey revealed that gully formations and sheet erosion accelerated, and in addition, shallow soil slides and very small rock falls occurred. So now let's look more closely to the post-fire processes. The degree of burn severity is the key parameter, and it determines the intensity of post-fire alteration. High burn severity indicates higher destruction of vegetation, soil structure, and produces more thicker ash layers. For this reason, post-fire emergency response teams generally track the high burn severity plots in the field to take immediate measures there. And remote sensing indices, such as the difference normalized burn ratio, which is the most commonly used one, help us quantify this severity, which can be linked to erosion susceptibility. However, it should be noted that without field validation, spectral indices alone can generate misleading results. And here you see the burn severity distribution verified with field observation points within a fire perimeter in Turkey. And the burn severity increases towards the orange and red colors on the map. And it's clear that burn severity is unevenly distributed. And the high burn severity level is not widespread. So we can roughly say that there is a moderate hazard potential. However, burn severity is not the only parameter to assess that. So the three routes are generally anchored to the uppermost weathered part of the ground profile, where the high burning temperatures take place. So therefore, the hydrological response to wildfire is very prominent and rapidly alters this part of the ground profile. The infiltration capacity and transpiration drops due to the loss of vegetation and the ash production. Eventually, overland flow increases. Therefore, even in moderate rainfall amounts, like daily 50 millimeters or hourly 10 millimeters, can mobilize large amounts of sediment. And the stability of slopes is also affected by the sudden hydrological response. As illustrated in the figure on the left, it shows the influence of both time and precipitation on the factor of safety values. And you will see that the greater drop observed in the post-fire period when compared to the pre-fire conditions, even under the same precipitation amount. So as I mentioned, field observations are vital to verify the burn severity determined by the spectral indices. Although there are several published guidelines and literature on the indicators of burn severity in the field and how it can be classified, these generally refer to the alterations in soil and vegetation. But for the rocky terrains, the description and classification of rocks, changes in rocks, have not been documented in a guideline yet. So, ash color and thickness, water repellency, and burning color of the vegetation are well defined in the guidelines. While for rocky terrain survey, the degree of spalling and cracking due to thermal fracturing, visual signs of any mineral transformations like calcination in carbonate rocks, and the inherent stoniness of the burned area would provide insight into the response of rock mass to the wildfire, and they should be also included in those guidelines. And soils lose more than just vegetation root strength after the fire. They also lose organic matter, which acts as a natural binding material of soil particles and increases the stability. In our work, focusing on the post-fire alterations in soil properties, we observed that where burning temperatures was low as 170 centigrade degrees, the fire didn't fully consume the organic matter. Instead, it burned the surface litter and the vegetation, and it added organic carbon into the soil. So it increased the organic carbon content in the soil. The interesting outcome was the significantly increased erosion, even at the low burn severity plots with this increased organic carbon content. So this led us question whether organic matter truly plays a key role in binding the soil particles. So through detailed and chemical and mineralogical analysis, we understood that the dominant binding agents were the calcite and iron oxides for our studied soils, and they were affected from even very low temperatures of burning. On the other hand, in moderate to high burn severity plots, with temperatures approaching 350 centigrade degrees, this aggregation occurred with an increase in fine sand fraction content. So you will see that resulted in a slight decrease. You will see the Moore-Clone failure envelope, slight decrease in shear strength of soil. And in parallel, the soil erodibility increased. Overall, these changes resulted in erosion rates approximately twofold the pre-fire levels. So actually, we can say that when compared to other Mediterranean regions, it's a minimal increase. I mentioned 500 times increment sometimes. So overall, these changes showed us there is a need to calibrate soil erodibility models for different soils and geographical regions with different burn severities. On the other hand, the most common, you should be more aware of it, the most common post-fire mass wasting process is debris flows, and which is generally sudden and catastrophic. And small-scale shallow slides can also be observed in the aftermath of the wildfires. While changes in soil due to burning have been widely studied, research addressing rock naturally burned by wildfire is still limited. Moreover, the impact of fire on rock and rock material and rock mass is different in scale. For example, rock material is typically affected at the outermost few centimeters, or even not centimeters, millimeters. In contrast, weathered and fractured rock mass can be impacted more deeply, especially along open or wet discontinuities, because the sudden increase in an escape of steam pressure cause rock to crack, even explode, and potentially leading to toppling or fall type of failures. And thermal shock can also cause rock spalling of thin flakes, and also in some cases, you will see in the middle of the image, some very large blocks can be exfoliated. Now, what are the broader implications of thermal expansion and contraction on rocks? Primarily, they generate microcracks, and laboratory experiments have shown that even at temperatures as low as 200 centigrade degrees, rock elasticity and hardness can decrease, and it leads to susceptibility to weathering and erosion. And several studies have found that heating to around 350 centigrade degrees can reduce the uniaxial compressive strength of rock by more than 20%. And another point is that the stoniness and the soil fragments on the soil surface, rock fragments on the soil surface. And these fragments can trap the transported ash, transported organic material, and clay also, and which in turn alter the hydrological behavior of the soil over time, and eventually contributing to the overland flow. But despite this negative impact of stoniness, it may have a stabilizing role. It can observe the rockfall energy and shorten the runout distance. And this topic has not been studied yet. And remote sensing, of course, plays a vital role in post-fire studies. We use UAV photogrammetry, LiDAR, INSAR to detect the deformation and quantify the erosion rates after the fire. And as Daniel mentioned in his keynote lecture yesterday, all the remote sensing technology we implement to monitor the slopes provides a different scale of insight in terms of temporal and spatial resolution, cost, and practicability. So in our latest study, we used INSAR time series to estimate the vertical displacement, and we refer to it as erosion. And we link this deformation with the spectral in optical remote sensing data like vegetation indices and burn severity, and also laboratory measured soil erodibility. So we obtained a comprehensive framework to study medium-term changes in the erodibility of soil. Nevertheless, the relationship between the soil erodibility and the erosion rates derived from the INSAR deformations actually very much affected by the spatial heterogeneity of the soil properties. On the other hand, the correlation between the erosion rates and vegetation recovery was stronger. So let's move on to the challenges we faced in post-fire hazard assessment. Yeah, post-fire effects are not spatially uniform, and factors such as lithology or soil type, slope position and aspect, burn severity and vegetation type produced highly variable responses across the landscape. For example, north-facing slopes typically retain more water, which can reduce the development of hydrophobic layers. In contrast, south-facing slopes tend to dry out faster because there is more solar radiation there. The south-facing slopes are more affected by wildfire than the north-facing slopes. Similarly, upper slopes are more susceptible to erosion than the lower slopes because of the gravitational forces. And in the photos you see here in the slide, taken from the unburned areas at the lowest elevations of the basin, we can observe gullies and shallow slides have occurred there, but these areas actually were not burned, and but they were impacted by the intense runoff originating from the high burn severity in the upper slopes. So this spatial heterogeneity complicates efforts to generalize erosion models and hazard assessment, again highlighting a need for site-specific assessment. One of the biggest challenges is the absence of pre-fire baseline data. Without information of pre-fire soil data or rock failure potential in the area, it becomes difficult to quantify the true magnitude of change due to wildfire. There are some well-known soil databases covering Europe and partly North America and Australia with coarse resolution as far as I know, but they can be still helpful in understanding the fire-induced changes. However, in many parts of the world, including my country, this information is absent. there are only point-based soil data that may be from 50 years ago, but still being used for the regional purposes. This is why establishing long-term monitoring, especially after the wildfire, is so important, not only to measure recovery, but to understand what has truly changed. And the integration of the post-fire soil data into the existing data sets would be very useful to forecast the dynamic condition of soil, especially with the changing climate. Apart from that, in areas where soils are young and therefore thin, and the rainfall intensities are relatively lower, gully formation may not occur. Instead, sheet erosion, as you see in the figure, dominates. And detecting the vertical ground deformation in sheet erosion, it's almost very few millimeters. It's really challenging to detect by remote sensing techniques, sometimes even in the field. So I have already mentioned at the beginning of my talk that the type, frequency, and intensity of hazards change over time. So this necessitates distinct risk assessments in short, medium, and long term. In the post-fire period, initially debris and mud flows dominate. After a few years, shallow landslides take over, and even decades after, rock falls may continue to occur. And if we plot this change, it follows a negative exponential decrease in hazard frequency and intensity. On the left-hand side, 15 published studies were evaluated to determine how many years after wildfires vegetation recovery occurs and erosion and mass wasting processes decline to pre-fire levels. The results show that vegetation recovery can take up to 60 years, while erosion and mass wasting processes may require as long as 18 years to fall below the pre-fire levels. And these findings altogether highlight that recovery rates vary widely depending on the vegetation type, soil properties, climate, morphological parameters, and the burn severity. And understanding this time-dependent behavior is essential for managing the geohazards beyond the immediate post-fire emergency phase. So let's move on with the future research directions. So future research must be transdisciplinary because the integration of different disciplines all provide valuable perspectives that can reveal the full picture of the aftermath of wildfires. And this collaboration should help also implement the knowledge into policies and regulations, and also guidelines for the very first step. We are also moving toward digital twin models that integrate field testing and mapping, optical and radar imagery, and real-time ground monitoring. So we can apply this dynamic approach into burn slope assessments also. In addition, post-fire rainfall thresholds that initiate the mass wasting processes should also be further investigated as they tend to decrease these thresholds immediately after wildfire and gradually increases over time. So as engineering geologists, we serve as a bridge between remote sensing and field verification, and we evaluate lithology, structural degradation, rock and soil characteristics, and our role is to interpret the multi-source data and translate it into actionable hazard maps. And let's now focus on the guidelines and policy making, where we can take, again, some roles as engineering geologists. Yeah, most national frameworks still emphasize debris flows and floods as post-fire hazards, but they generally overlook the less frequent rock and soil slope failures. However, as the intensity of fires is increased and the urban areas are expanding, even less frequent and small events will pose a risk in the future. So these frameworks also generally focus on the first year, right after the fire, but we know that the hazard potential persists beyond this time period. So comprehensive guidelines should integrate erosion, shallow sliding, and rockfall hazards along with both short-term emergency and also long-term recovery monitoring. And achieving this, of course, requires strong collaboration among public agencies, academic institutions, and local authorities. And these improvements and collaboration also align with the United Nations Sustainable Development Goals, especially with the SDG 11, SDG 13, and SDG 15, with sustainable cities, climate action, and life on land. I think I catch up the time very well, right? So, and the concluding remarks are very briefly, wildfires reshape not only the soil, but also the rock slopes, and their impacts are especially heterogeneous and can persist over extended periods. And technological progress offers new tools, but true resilience requires field-based verification and understanding. And my last message is every burned slope tells a story, and our task as an engineering geologist is to read it before it becomes a hazard and have a stronger voice in developing policies and regulations. Thank you for your attention. And
Thank you very much for this really interesting presentation. That is the last of this session. Before closing the session, I have to invite all the speakers to receive the certificate from the organization. Yeah. So I invite Professor Muhammad Kumrul Hassan. I invite Professor Shahid Azam. Professor Giovanna Vessia. Professor Tumai Kadaki Koka. Yeah, I think we can. Group photo, yes.
Now I would like to request Dr. Tundiraj Pathak, Vice President, Nepal Geotechnical Society, to please come up on the stage to present the token of appreciation to our chair and co-chairs. आउनु न, आउनु न। हुन्छ, हुन्छ। Thank you, sir. Thank you, session chair and co-chair. I have few announcements to make. So whoever have a presentation next, I would like to request you to please give your PowerPoint to our volunteers waiting outside. And also to the attendees, you'll be receiving a digital certificate from the organizer, so by email. So if there is any changes that you would like to make in your email, please contact our volunteers team. Thank you. We'll begin the next session at 11:30.
realizing as
Hello, your attention please. We will now begin the parallel technical session 14 in this hall with the theme landslides and AI in engineering geology and sub-theme AI for engineering geology, recent advances and emerging frontiers. So for this session, I would like to invite Professor Ashok Dahal to be the convener of the session. And I'd also like to welcome Mohammad Farooq Hassan and Sarup Audel to be the coordinator for the session. Thank you. Over to you.
Hello? Thank you. Hello everyone. Welcome to this session. I think some people are still enjoying coffee break, so let's start. I think that because we are already a bit late. So for the first invited lecturer in this session, I'd like to invite Professor George Papathanassiou, if I pronounce it correctly, for his presentation on enhancing liquefaction hazard forecasting on regional scale. And you have 20 minutes.
Thank you very much. So, good morning. I would like to thank the organizing committee for the invitation to present our research regarding liquefaction phenomena and how we can proceed to an accurate forecast on a regional scale. I would like to acknowledge my colleagues Sotiris Valkaniotis and Maria Tavtsoglou, who contributed in this presentation. So, as we know, liquefaction can be considered as the soundless earthquake-induced hazard compared to landslides, co-seismic landslides, and tsunamis. We can see on the left side of this slide an image from the video captured back to 1964 in Niigata Airport. And on the right side, some images from the 2003 Lefkada earthquake with the damages caused by the co-seismic rock slopes on the urban environment. So we must not forget that one of the most largest container ports in the world, the Kobe's port, was heavily damaged due to liquefaction-induced failures to port facilities and dropped from the 6th position to the 28th by 2013. So the milestones regarding liquefaction research, we can say that are the Niigata earthquake and the Anchorage earthquake in Alaska and USA back to 1964, Kocaeli, Turkey, and Chichi, Taiwan earthquakes in 1999, obviously the seismic sequence in Christchurch in New Zealand, 2010-2011, and finally regarding the latest, how we can go back on this. Okay, and finally, the two earthquakes occurred in Kahramanmaraş, Maraş, Turkey, 2023. So the first milestone is related to the Niigata mainly earthquake back to 1964, and after this event, researchers realized that they must further study liquefaction phenomena and why this event effect occur. So we can see here on the on the left side a very well-known image of the tilting of buildings in the area of Niigata, the collapse of a bridge, and on the right side we can see the flow failure occurred in Anchorage, Alaska, USA. So the second milestone, as you know, is related to the two earthquakes occurred in 1999 with tilting of buildings in the city of Dapazari and a lot of damages in several cities in Taiwan. After that event, after both events, a large amount of data provided by in situ, mainly CPT and SPT, and laboratory tests conducted in sandy, silty sands with high fines content and silty soils of low plasticity give the opportunity to the scientific community to revise the existing liquefaction susceptibility criteria. It was very important because we understood that also silty soils of low plasticity can produce, can trigger liquefaction phenomena. And finally, you all know the seismic sequence in Christchurch, where almost all the central part of the city, the central building area, was heavily damaged due to liquefaction and covered by the ejecta. So these are the three events that we can say that was a motivation for the scientific community to further examine this phenomenon. Regarding our research, the motivation was an earthquake occurred back in Greece in 2021, in the central Greece. As you can see on the left side with red dots are the sites of liquefaction as they have been mapped by our group. Follow the river of Pinios, one of the biggest rivers in Greece. And on the right side, we can see some paradoxo, as we say in Greek, although the fact that the surficial geology, as has been mapped in the official maps of Greece, is covered by alluvial, we can see that on the eastern part of the map, the density is much higher than the eastern part. So we try to understand why this happened, and if we can see on this, we can focus on this rectangle, in this square, we can see that the liquefaction sites are not related to the present-day river path. We can see that these clusters are probably follow something else. So trying to understand this, we go back in time about 80 years, and we were very happy, allow me to say, that we found that based on orthophoto from 1945, where we can trace the paleoenvironmental features like the oxbow lakes, meander belts, and abandoned channels, that all these clusters of liquefaction are strongly related not to the present-day river path, but to the paleoenvironmental, to the abandoned channel deposits, point bars of meander and oxbow lakes. So we would like somehow to correlate this, to find this correlation, to investigate this correlation between the distribution of liquefaction phenomena with the surficial geology, and if it's possible, to correlate this distribution with the types of sediments that can be found on point bar formation. These are the cases that we took into account, the case in Christchurch in New Zealand, the case in Greece, in Damasi, and the cases after the Kahramanmaras earthquakes in 2023 in Turkey. So we all know that liquefaction phenomena occur with higher concentrations in specific geomorphological formations. So what we have to do, we have to find a detailed map of geomorphology, or if we cannot find a map of specific geomorphological features, then we must develop one. If we have this type of maps, then we can apply one of the most well-known procedures, the pioneer work of Youd and Perkins back to 1978, or some other methodologies from Wakamatsu, Japan 2001, or from USA, mainly in the area of California. So applying these procedures, we are able to assess the liquefaction susceptibility, but not to quantify the susceptibility. And the question is, can we put some numbers on this? Can we somehow give a probability on regional scale of liquefaction susceptibility? Because if we can do this, then we can accurately predict the liquefaction sites in a future earthquake. And the most important thing is that we can assess the risk of critical infrastructure to liquefaction. So let's start this. I will now start showing the results of our study, of our works, initially regarding the correlation of the distribution of liquefaction phenomena with the surficial geology and geomorphology. So in every case, we had to map using satellite imagery, as we presented 2 days ago for the Myanmar earthquake, 2025. So we had to create this map, and we have to create also the detailed superficial geological map. If we have these two basic parameters, then we can statistically analyze the results, the distribution of liquefaction phenomena in correlation with the geomorphological type, using this equation that you can see in the middle of the slide, using the density of each geomorphological formation versus the density of the total study area. As we know, in an alluvial plain, we can find different types of sediments. So in order to harmonize our results, we decided to group the sediments in three categories: the abandoned meanders and the channels, the point bars, and the floodplain type of sediment. So the first case was the Kahramanmaraş earthquake. We presented the procedure that was followed in order to detect liquefaction phenomena using satellite imagery, starting from the Sentinel-2 images up to more detailed images like a planet, and on the right side, able to detect the liquefaction phenomena that occurred after these events. So focusing on the area of Asi or Rondes Valley to the southern eastern part of Turkey, close to the borders with Syria, we were able to detect in detail the location of ejecta and to map, to delineate the areas affected by lateral spreading phenomena. So this is the final map regarding the location of liquefaction phenomena, and the next step was to compile a detailed geomorphological map on regional scale. So in order to achieve this, we use the digital elevation model in order to be able to map low relief zones, satellite images like Corona back to 1970, and the images provided by Google Earth and Maxar comparing the pre and post-event situation in this area. Finally, we were able to create this geomorphological map, as you can see, showing the location of liquefaction phenomena and lateral spreading in comparison to the three basic geomorphological features: point bars, abandoned channels, and floodplain. After that, we apply this equation, we statistically analyze the results, probably, obviously with the GIS, and found that point bars are the most favorable sediment in order to trigger liquefaction phenomena, followed by the abandoned channels and meanders. The same conclusion, more or less, was for the lateral spreading phenomena, where point bars and abandoned channels and meanders were the most favorable types of sediments in order to host these failures. Similar procedure followed for the Piniada Valley in Greece and the Avon Valley in Christchurch for the two earthquakes, 2010 and 2011, and you can see how we were able to compile a detailed geomorphological map. In the case of Christchurch, we were very happy because there was a very good job done by colleagues in New Zealand, and the geomorphological map was already compiled. So as a result, regarding the geomorphological formation and the correlation with liquefaction phenomena, we can say that the ejecta, ground fissures, ejecta, sand boils, sand craters, all these type of phenomena very related to point bars and less related to floodplain, older sediments, while the lateral spreading phenomena are also related to point bars and abandoned meander, and lesser to the floodplain, either younger or older sediments. The second topic in this research was to try to find if it is possible to further analyze the point bars in different types of sediments. And in order to achieve this, we follow an application proposed by Russell 2017 regarding the different types of sediments that can be found in the area characterized as point bars. So we have to find the geometrical features of meanders, classify the meanders and point bars based on their evolution. And finally, as you can see on the right slide, at the bottom of the right side of this slide, try to distinguish 4 different types of sediments per point bar, starting with the type 1, which is a coarser material, and up to type 4, which is a most finer material. So we did this work for the 3 cases, focusing only on point bars. You can see on the left up side the case of Piñada, on the right side the case of Asi or Rondes Valley, and the bottom the case of Chrysler's Avon Valley. So as a result, regarding the different types that can be found on point bar features, we can say that ejecta phenomena were related to the first type, which is the coarser material is the dominant type of grains, while lateral spreading phenomena, and this is a paradox in our case, it seems that are more related to the finer material, but this paradox has to do with the specific geomorphological environment in the Asi River, where we have a small inclination of the banks, and probably this is why we have this not expected result in lateral spreading phenomena. Okay, we were able somehow to give some numbers. It's just the beginning of our research, but the question is, how can we use these numbers? How can we use this methodology to go one step further to assess, if it is possible, the risk of critical infrastructures on regional scale without be obligated to conduct any in situ test, because if we have CPT or SPT, we can easily estimate the potential per site. But is it possible to provide a preliminary assessment of risk based on regional scale and to decide where we can construct, for example, an airport? Because as we see, airports in Niigata, in Loma Prieta earthquake, in Nisqually, in Tohoku, and in Turkey have been damaged by liquefaction phenomena. And these damages were related to sinking or shifting of runways, taxiways, and ramp areas, ground deformation, different settlements. So airports are one of the most vulnerable structures in liquefaction. Obviously, like port facilities, but the airports are more crucial for the recovery phase after an earthquake. So here we can see a map provided by USGS regarding the location of the Kings County International Airport in Washington that was heavily damaged by the earthquake back in 2001. We can see on the left side the location of the paleo meander of the abandoned channel, and on the right side the location of the constructed airport. So it's clear that the airport was constructed upon a paleo, an abandoned channel, which is one of the most favorable, susceptible to liquefaction phenomena, type of geomorphological sediments in this zone. So I will quickly present this phase of our study. We try to create, as I have previously presented, the geomorphological map, try to assess liquefaction susceptibility per type of sediment, create liquefaction susceptibility map, and then try to estimate the risk. In order to achieve this, we use the methodology proposed by Hazus, starting with the probability of to liquefaction of the sediments, the estimation of the permanent ground displacement, and finally, estimate the direct loss in case of an earthquake that can trigger the liquefaction. So the example that I'm going to show is the one from Greece, from northeastern part of Greece. The international airport of Kavala was constructed back to 1980 80s, but it was constructed upon an abandoned channel that was covered by human activities, that was covered by agricultural activities. So they didn't know, they didn't make any geological, let's say, study in advance in order to identify, to delineate exactly where was the abandoned channel. So as it has been previously presented, we follow all the steps 1, 2, 3, and 4 in order to be able to assess liquefaction susceptibility, create the superficial geology map, create the liquefaction susceptibility map, and you can see on the bottom of the right side that exactly the runway of the airport is located upon the red zone, the zone that shows the highest susceptibility to liquefaction. After that, we were able to, based on the HASUS procedure, to estimate the probability to liquefaction of the very high and moderate susceptibility sediments, estimate the permanent ground displacement, and the next step and the final step was to estimate the direct loss and give some number, give some cost in millions of the loss that could be related to liquefaction if it occurs in a future earthquake. So, finalizing the results is initially regarding geomorphological formation is that the spatial distribution of liquefaction phenomena clearly indicates that one of the most susceptible to liquefaction geomorphological features are the point bars. The laterally discontinuous depositional behavior of point bars differentiates the preferential behavior of the area to more or less likely to host liquefaction. Regarding the point bars, we have to say that the correlation between the pattern of different lithophases with the liquefaction ejecta and lateral spreading phenomena indicated that most of the effects were triggered in deposits mainly consisted of coarse and sandy materials. Quantification of the relative effect of different geomorphologic environments on liquefaction phenomena can be an important step toward developing enhanced predictive model for liquefaction-induced ground deformation. And finally, in the aftermath of an earthquake, an airport is a basic infrastructure for the first phase of recovery program. So it is crucial to re-examine the vulnerability of these structures and to estimate the risk, because we know now that in case of this type of sediments, we must take into account the susceptibility to liquefaction. But what about the structures that have been already constructed? Shall we leave these structures without any further attempt to increase the safety of these structures, or we can just wait for the next earthquake and map again the liquefaction-induced failures to the critical buildings of an airport? So thank you very much for your attention.
Hello. Yeah, sorry. Thank you very much for your quite nice presentation. For questions, I think maybe we are quite running late on time. Maybe we can ask the question. Yeah, okay, then you can come here.
Namaste, Professor. I am Triveni University, Dinesh Raj Sharma. What key geological parameters influence must improve in your regional liquefaction hazard forecast?
Geology is the first parameter for liquefaction. It's very simple. The first of all is geology. So we have to map in detail the different geomorphological and superficial geological formation. This is the most important thing. And be able to give a date, because late Holocene from Holocene sediments have behaved differently. So it's crucial to be able, instead of having one map showing alluvial plains everywhere, to be able to say point bars, abandoned jars, crevasse plains, floodplain, because after this detailed mapping, everything can be estimated. But without this, then we have a regional scale without numbers, a regional scale map where most of the alluvial plains are red, meaning very high or high susceptibility. But this is not the point. We are in 2025, and we must be very accurate in what we give as an outcome, a deliverable on a project regarding liquefaction or regional scale.
Hi, George. Very quick question. Yeah, geology, of course, and hydrogeology. Could you comment a little bit on that? When you have borehole data, groundwater levels, how could it help you?
This is a difficult issue because a fluctuation of the groundwater table depth, we know that happens annually. So, and it's not, the solution is not saying that we are going to get the worst case scenario, meaning that everything was flooded. So, and it's very difficult to have a reliable map showing exactly how the groundwater table depth goes every month. So it was suggested by several authors to use the ground table depth up to 3 meters. But in my opinion, if we have piezometers or we have other hydrogeological related data, we should obviously use them. Because geology and hydrogeology are the two steps in order to walk on this liquefaction path. And the earthquake, but okay, this is for the seismologists.
Yes, thank you very much for your presentation and your answer to the questions. So the next presentation is by Ji Do from precursors to runout, deep learning, crack mapping coupled with SPH landslide dynamics. So you have 15 minutes, and in 13 minutes we'll ring a bell, so you can wrap up.
Go back. Okay. Good morning, everyone. My name is Jie Dou from the China University of Science. Today, I would like to share our recent work. So today, I want to talk about we use the deep learning. From the precursor to the route AI and drive the crank mapping coupled with the SPH simulation of the landslide dynamics. So before start my talk, I just want to introduce my group. I also got my tuition to later will give a talk. So I just introduce my research group. We focus on 3 research directions. First, based on the water, the area. So we use the module source data, try to do the landslide detection Johanna. And for the single Johanna, we also do the crank and the mapping. And then we find the location of the Johanna. So we do the reg segment. And for some important Johanna, so we try to impose the maximum. And then for some of the single Johanna are potential to the like a dam or some property. So we try to install sensor to do the IoT monitoring and also do the digital twin vertical larger models. And okay, let's start my talk. Include the 6 parts. First, background. So from this figure, we can see and the landslide, the local in the world, also in China, and this some event caused the serious loss in the world. And this figure shows that China, the person is shown on the global, the landslide location. And we may know China is one of the most country with the one distribution and most severe impact from the landslide. And the landslide seriously impact from the public safety and social, economic, and development. And presently, China is just one of the landslide distribution. But according to our global leader, academic in the town, he said China is we remove one, we are the largest and the landslide distribution in the world. So these 2 figures show that the sum and the landslide in China caused serious damage in the world. And from the global to the China, now it's Three Gorge area. Maybe you know the Three Gorge Dam. And because our university, we located on the Yangtze River in the Three Gorge area. So Three Gorge area, due to the reservoir, the water level, I mean, there are centimeters and flagellation and heavy rainfall and the landslide. Okay, I just set time for reminding. Okay, and it's been very complex and I mean, like the formation and mechanism and very difficult to identify the evolution state and low prediction accuracy. So and now the TR, I mean, the Three Gorge area is the key that hub of the Yangtze River economic belt. Maybe Yangtze River is very important. It's the largest river in China, and the landslide seriously affect the safety of the China, the major engineering property, and also the implementation of the national street, and why we studied under, I mean, like the landslide in the Yangtze River. And the research, I mean, like we have three objectives. First, like the technical and the theory and the application. For the technical, I mean, we do the broad through the network of early identification of the landslide deformation features such as the crack. For the theoretical, we studied the interstability mechanism of the landslide on the different triggering factors. And finally, we do the application, build the dynamic model of the entire landslide evolution process, revealing the kinetic characteristics. Next, the character, I mean, like for the crank features and the crank, their distribution, reveal the landslide evolution, maybe like the first step or the first state, and the second and third, okay? And the following and the stability, rainfall, connect the crack, reduce and the slope stability. For the kinematics, we can understand the full movement process is the key to the risk assessment. And we do that the ground cracks are very important, is very crucial for the deformation. I mean, like the staging and the early warning system. So we bought in my group, we bought 4 high UAV and we use UAV imaging. We do that, we get all the photos, like the DM is very widely used for the deformation. So this figure is we published the one paper. So the following is the reference. You will know the details. Maybe you can refer to this is the ZO1 journal. And for traditional, I mean, like there are many that like cracks, so it's harder. We use to manual interpret. So, and now the deep learning also want to use for the object landslide or crack, the identification. So we also published some of the articles like ZO1 and the top journal. So if you're interested, also we can follow to the reference. Also, my student yesterday gave the post. Yeah. And the trigger like the quakes, the rainfall or human activity, significantly alter the topography. So landslide morphology varying greatly over the time. So we also do that over 20 years for the landslide evolution. We use land vegetation and recovery. I mean, we also published some of the journal and also honor is the reference. I mean, so if you're interested, maybe you can read. For the slope instability, so I mean, like it's very common metric, but often used as the average parameter. For the reliability, we must consider, I mean, like the parameter, the variability, even just the single landslide, also the C value of C value or phi value are different. So, and the probability of the failure, PF here, for the is very I mean, like it's very for complete analysis. So, and for the dynamic simulation, is also very important step for the risk assessment and the mitigation and the design. So for there are many methods such as PFC, or we use like the mass flow or mass DM. So in our case study, so we use like SPH, like smooth particle hydrodynamics. This is a very fridge and method. Added for similar the large and the displacement. So study area. This area is located along the Yangtze River. and their slope is over around 20 degree, and their dimension, I mean, like fan shaped. So I mean, also the area and the volume. So that this is the larger than the scale. I mean, mix the rock and then like soil. This is the mix of the land sand. And for the geology, I mean, like the most for the sand body is mostly CLT clay and topsoil, and the rock fragment is very land sand pro layer in Badong. I mean, like the Langyang River is very special and formation layer. And the slime zone is this is the deep sea land sand around 20 meters for the depth. Yeah, and along the Triassic Long Badong formation interface, the rainfall max is in 2020 over 300 millimeter June. So I mean, we collect many different multi-source data, such as the geology, topography, lithology. We also do the several times for the UAV and like field data, and collect and we get the DM or DSM and also the ladder data. And for the method, also the rainfall. And for the first flow, we use like intelligence for the crank, we use the deep learning method. And for the stability and the variability analysis for the process, for the dynamic simulation. And for the, I mean, we conduct 5. This is just the 5. Actually now over 5 detailed field surveying, and acquired high frequency and autorophotos and 1 DM and 5 DSM analysis. The long-term the resolution use and the multi-source imaging with this. Okay, sorry, go back. Yeah, each time I bring my bag, and each time after rainfall, I go to this site and do to measure the crack. For the crack identification, so we use SUNet, also compare the traditional deep learning like UNet, the model. For the stability, we use like the limited and equilibrium method, REM, for the factor and the safety. For we also use the model for the like the failure probability under the extreme rainfall. I mean, for the simulation, we use the SPH, try to simulate the full process and run out and their velocity. So the result, and we provide and we developed, and the different crack show that maybe this just display the different and the state of the land sand, like like a well-developed teaching crack are rare escape compression crack at all. So I mean, like we try to develop and to quickly identify the crack and to try to understand the state of the land sand. And we combine different methods, and we provide the UNet outperform than the traditional UNet, and match our field work. And we also developed, we not only developed method, but we also developed the software. So we developed the multi-model, the land sand crack identification software. We use the optical imaging, LiDAR data, and INSAR. And we also, and I mean, this is just the interface of our developed this software. And maybe if you want to use, maybe we can provide that. We also give the company to use. And for the natural state, like FS, factor the safety. For the natural state, is very, I mean, it's stable. And sorry, after extreme rainfall, it's over 320. So we can see, and the factor safety is seriously increased, means unstable fear. So for the maximum, rainfall infiltration, raise groundwater, and increase pore pressure, and reduce and shear strength. This is shown on the sketch of this, how landslide occur. And the landslide phase stage, we developed the 4 stage. The first is the infiltration and the crack, the development. B showed on the sliding and the partial, the locking. C is showed on the failure, The final one is the accumulation. And according to our numerical simulation, and the total duration is around 15 seconds, and the maximum deposit is 5 meters. And finally, I mean, like we totally, find the deposit is around 15, and so at the toe or a slope toe near the residential area, so it's very dangerous. Maybe it cause the loss to the local people. For the velocity, and the first increase and then decrease blocked by the building, the maximum velocity is around over 20 millimeters per second, at the time is 19 seconds. Discussion. So I mean, we do the multiple temporal UV DSM data, and to quantify the micro deformation. The results show that some DSM different than the slow erosion decrease and deposition increase. The largest erosion in around 2023 to 2024. Also, there was some other. We also discussed maybe there was some other outline. Why? Maybe because of data, some data and the problem. And for the simulation, I mean, like we use under the volume model, like the turbulence, and we said 200 to 500. For the technical cycle is 0.5 to 0.25. The results show that the high turbulence, the longer the run out. Thinner deposition, high the fraction means that the short run out and the deposition at all. So summary. So based on our material source data, so we do the simulation, and we also do with grep and how to automatically detect the crack. We also not only just the direct, we also calculate the length and the width of the crack. And for the stability, after the rainfall, so then the failure probability increase from the 20 to 95, almost 4 times. And so the reason it causes the rainfall infiltration, raise the water table, and increase the pore pressure and reduce the stress. And we use that numerical model. We can also to reply how this landslide occur and the depth of the deposition, the velocity. So this research can provide a key technical support for the landslide disaster. I think almost close. I mean, just finally, I show some developed some of the software. I mean, we all in my group at my student, we also developed. We combine the multiple source data and combine with the physical model. We try to develop and then the. We basically use the large scale geological disaster based on different experts, such as geological disaster or landslide accident. We can make the different, like the result. So it's very useful for the local and geological theory. So maybe, we can use then the DeepSeek or ChatGPT. We can use their token and try to develop this. We also buy them like A100 and the GPU. And we also developed some like the risk software. We combine with traditional and expert methods such as AHP, statistical method, or also such as like the center factor or information value, and we do the machine learning like SVM, and we also use the deep learning combined with the physical model. Finally, we developed this software. We do the digital twin. How to predict, we use the dynamic threshold to predict the rainfall induced the landslide. Finally, this, because this journal is belong to our university, this is now belong to the GCRQ1, so if you are interested, welcome to submit. I think this is a good journal. Not only belong to our university, also belong to the world. I think welcome to submit. Finally, this is the first, okay, I will soon finish, okay. This is the space, air, ground, the deep, and the tunnel. We deep the tunnel along the landslide. So I think here some of the research have been with our this and the tunnel. like Professor Jaworski or some the other professors have been to there. So welcome to do some of the collaboration. If you're interested, I think this is very special. You can see that some of the, some of the very micro, the landslide feature, like the sliding body, etc. Finally, almost close because time is very limited. I just, if you're interested, we have an official account. So welcome to Scan. Okay, thank you for your attention. Oh.
Thank you, Professor Jigo. I think we are running out of time, so if you have any quick questions? No. So thank you very much. Thank you for your time.
Thank you very much. Thank you. Now I welcome Mr. Ashok Dahal for his presentation on slow-moving landslides modeling using physically informed neural network. You have 15 minutes. At 12 minutes, the first one will begin.
So I'll try to be as short as possible because we are running a bit late. So my presentation today is going to be on physics-informed neural network and how you can use it for slow-moving landslides, also like how to map them, like stuff like that. I'm Ashok, as the convener introduced me. I'm a assistant professor of AI for early warning systems at the University of Twente in the Netherlands. So let's start. What I'm going to talk is a bit about slow-moving landslides. What are they? I think everyone here knows what slow-moving landslides are. Deformation on slow-moving landslide, which might be a bit new. And then neural networks, which I think this is a session on AI, so most of you might know. And what are physics-informed neural networks, pins for slow-moving landslides, and a bit of a discussion on that. So this is, if you look at the background, this was a slow-moving landslide in Turkey. And during the earthquake, it failed. But after that, it started moving. So the upper part, you can see some cracks. Maybe I can use the pointer. I don't know, the pointer doesn't work, but there are some tension cracks. You can see it later on. So this whole presentation is going to be on the pre- and post-seismic slow-moving landslides in Turkey with the Kahramanmaraş earthquake, if I can pronounce that correctly. So what are slow-moving landslides? So you know what landslides are. There's landslides, but they're moving very slowly most of the time. But sometimes what happens is the friction is not enough to hold it, and they start moving slowly, and at a certain point, they lead to a catastrophic failure. The slow movement can be for thousands of years sometimes, or maybe very rapidly within few days, like the oscillation goes within few days, and then it starts cracking. So how does it move is you can have a decrease in the shear strength and also increase in the shear stress. Many things can affect it, so many things such as alteration or weathering of the factors. So I took this picture from Lacroix et al. 2020, Life and Death of Slow-Moving Landslide. Really nice paper. If you have time, you should read it. And like groundwater and pore pressure change, which is caused by it. In rainfall, if you make sewage, if there is other cracks that flows the water inside, vegetation removal, and then the increase of shear stress can be debuttressing or loading if you make a house on top of slow-moving landslide, if you do a lot of vegetation or do other stuff like, let's say, earthquake, which is, we don't really have a control on that, right? So how does the deformation look like is in an ideal scenario, let's say in a very generalized case, you have time in x-axis. So over time it keeps deforming. Initially it's 0, so there is no deformation at all, so there is no landslide. Then it starts deforming slowly, slowly, slowly. And at a certain point, it goes to very isolated deformation. So shown by orange color there. It looks red there, but it should be orange. But so it starts isolation very fast and then leads to a catastrophic failure. So, but in reality, it doesn't happen like that. Like it's not very simple, like very straight line that goes to the failure. We have many seasonal variations, many stress loading and other stuff. So over time, you have like some deformation, slow down, and then you have a very isolated deformation, which leads to a catastrophic failure. After that, it can completely stabilize. So it can say, okay, all the mass that had the possibility to move, moves out. There you have a failure, a landslide, big landslide, or it can still have some of the mass removal and then you have more deformation afterwards. Like the picture I showed you in the beginning, it was a very slow moving landslide. 2023 earthquake happened, the landslide occurred, so then some of the masses got wasted, but then there are still some more mass that is deforming now, that I'll show you in a bit. So that's brief introduction, and this is a conference on engineering geology, so I shouldn't talk a lot more on the landslides and why it moves. I think most of the people know why it moves, right? So let's talk a bit more on neural networks and PIN. So what are neural networks? You know, people are always talking, oh, AI, it will kill us, it will do blah, blah. But at the end, it's just a big matrix, or you can say it's a big function, right? So this is a very common image that is used for neural networks. So, and then all the things that are called like neurons and connectors and stuff, they are all big metrics, and then you just keep multiplying them. And it's a very, let's say, brute force approach to solve any problem. So if you want to solve a sinusoidal equation, like a sin x, it takes a lot more parameters than just one very simple function. So, but these are called based on the universal approximation theorem. So these are, so what it states basically is the neural networks are universal functional approximator. So what does it mean is if you have a complex enough neural network, you can convert it into any function that you desire. So it can be a very non-linear function, it can be sinusoidal function, it can be tangent function, any kind of function in the world, you can represent with enough, let's say, depth and width, enough complexity in your model. Because in neural network or AI, you do not really define the function. Let's say Tergaz's equation, let's say for the soil mechanics. What you do is you don't define the function yourself. You have data, you have like observation, and you have the factors that can control them, and you learn the function. So you try to model. So the neural network models are actually just a big function that you optimize based on the data set that we have. Then this is just a neural network. You have X and Y, and then you make these functions. But what are pins then? What is the difference between a neural network and physics-informed neural network? So I put the photo of soil mechanics here. I could have put also Albert Einstein, but anything that is physics. So what do you do is basically with the neural networks, they don't understand the process. So they are quite good, very powerful, but they don't understand what landslide is. So you give a lot of data and train them. They can predict or let's say mimic the landslide, but they don't actually understand. The model doesn't have any constraint on what landslide can be. So if you have a bad model, it can give you one of the examples that I had was someone trained a model, and the volume of landslide they predicted could be 5 million cubic meter in the SCAR, or in the initiation zone, which may be the case, but looking at the terrain and the geomorphology, that's not likely the case. So it has some bounds. So the physics-informed neural network puts some bounding conditions, or let's say some guiding mechanism of the failure, so that we can have at least, we can mimic the landslide, or we can say we can predict the landslide, but with some physical sense, or let's say that at least looks like true landslide. So how do you model them is mostly you can use the stress-strain equations, or you can use the strain configuration, but we don't really know, we don't really measure the strain if you want to look at the regional scale. If there are hundreds of landslides, we don't have the instruments to always capture those values, right? So we do this, at least I did this, with deformation, because that is the direct representation of the strain. Because if you observe the deformation from satellite, what it means is there is some movement going on, there is some physics, and it has plastic deformation that is irreversible. So if it is reversible, it's already gone within few minutes or few hours. Then you cannot capture through the satellite, but through the satellite you can, let's say, look at the long-term plastic deformation. Not always, but with some let's say, caveats. So we calculated, we mapped the deformation in 2023 Turkey Kahramanmaraş earthquake-affected area. This is, we used INSAR, so we used 6 tracks and many frames. So it was like, I don't know, maybe 20 terabytes of data that we processed. This work I did mostly at JPL when I was there in NASA. And then we have the geology and all the controlling factors to understand this. So what we did, the first thing, I'll show you two stuff that I did here. The first is to understand how the geological strength changes. So we didn't really try to model the landslide here. We have the deformation, so we have all the hill slope deformation that we have observed, and we wanted to use the neural network. I told you before it was a universal functional approximator as an inverse function. So what we did is we have the deformation, which is observed. We have the geology and a bit of, let's say, strength parameter, which is a bit of a stretch because we extrapolated those. And then we use the neural network as an inverse function to estimate the GSI before the earthquake and after the earthquake. So geological strength index, which you should go to field and do a lot of observations to measure, but we just made this to predict, let's say, with some uncertainty, of course. And using the same model, we also did it for the post-seismic case and checked if there is actually hill slope strength reduction, weakening, or strengthening. In some cases, like we saw in the literature, there was cases of strengthening as well. And we can see the distribution over here for each mountain slopes, right? So you can see most of the times it's just weakening, and there are few locations, the density plot, which is very exaggerated, so you see it a lot more clearer. It's not like everywhere it's weakened. So you can see like there is weakening in most of the places, but strengthening in very few locations. And to see why is that, we looked on into geology and the factors that can cause it. We also did this with the numerical solutions, actually, with finite element to test. But I'm just showing the neural network part because that's what the presentation is about. So we see most of the weakening happens in all geological classes, actually. And if you look at sedimentary, there are very few locations where the strengthening happens. Tiny bit green, it doesn't happen a lot. It's mostly weakening. Like if there is an earthquake, it doesn't make the hill slope stronger. But it can do sometimes because it can reconfigure the material directions, right? The orientation of the material, it can shake it and then makes it a bit more stronger. And most of it was controlled by the aspect, like how the orientation of the material is, which has to do with the deep angle and stuff like that. And also a bit of a PGA. So if you have very strong shaking, it doesn't really make it stronger, always makes it weaker, but within like 0.4, 0.5 G range, we have a bit of a strengthening effect. Now, I promised landslide in the beginning. I got a bit of a derail in the middle, so let's look at some landslide. So from the same INSAR data that we had, we identified landslides, so we mapped them. We mapped all around Turkey, and we also give them like what is the confidence interval, what is the confidence level, what is the exposure, and the overall geomorphology. So we went to the field, checked if there are landslides or not, and we categorized them as pre-seismic, post-seismic. So the hill slope that were stable before, stable afterwards, we don't consider them. And we see if they were moving before, and if they are stable now, they are stabilized because it failed or something happened there. And then if it is moving now, it's activated. And if it was moving before, moving now, it's just moving. We classified them, and then we have the deformation you can see. There are tension cracks. This is just to show that we went to the field and had a nice time there. But you can see like there are a lot of tension cracks that are visible in the locations that we detected, and we see the time series. And we try to understand why they happen. And it was, again, the peak ground velocity, which was controlling this behavior of the models. Because we have, I think, 1 minute left. And then we also try to predict the deformation pattern in the future, also using physics-informed neural network. But this is still work in progress. It's not really finalized yet, but given a shape, you can predict the velocity, how it will move in the future. Also constrained by physics, but the accuracy is not yet what I would like to be, so it's a work in progress. So what are the challenges and way forward is, like landslide is, even though it's usually like in the geoscience community, we are very small, it's very complex problem. Like you have multi-physics, you have soil mechanics, then you also have triggering mechanics. You need to look at what is the evapotranspiration and stuff like that, earthquake mechanics where you have shaking. So it's much more complex than many other problems are. So you need to integrate multi-physics, and then regional scale geotechnical information is not really there. We extrapolated it based on the geological map, so we don't really have very detailed borehole information, which I would like in maybe 500 meters everywhere, but nobody has money to do that. And better integration of triggering mechanism. And the displacement here is from INSAR is in the line of sight direction. So satellite comes, looks at it, and then goes. So the deformation that we monitor is only in the direction of the satellite that you look, okay, this is the direction. If it is in any other direction, it cannot really detect. Like if you have north-south direction movement, forget about it. So the displacement, but actual displacement in the field is always in 3D, right? So we don't really integrate that, and then that's much more complex to integrate. And also near real-time modeling. This is very far future that we need to look at in maybe 10 years, I don't know. So thank you, and let's hope the slow-moving landslide that we monitor, we can predict them before so that people don't get lost or then died or get killed. So thank you very much. If you have,
thank you.
If we have time for questions.
Thank you, Mr. Ashok Dahal. Any question? We can take quick 1 or 2 questions, please.
Yes, thank you. Inspiring. You're talking only about the deep-seated landslides, right?
Yes.
I think it's important to say that.
Yes. Yeah, these are all deep-seated landslides because the resolution that we are monitoring at, you cannot really detect the small shallow landslides. These are because 30 meter by 30 meter resolution, so you need at least, let's say, 10 pixels to monitor, which will become around 300 square meter landslide. So anything less than that is mostly going to be swept away in the noise of INSAR. So, yeah.
So we can take another 1 or 2 questions. Still we have 1 minute. Any more questions?
Doesn't seem like so.
Oh, please.
Thank you for the talk. I want to know if you do that the single or deep sea or for the wider area. I mean, because for the geotechnical and the parameter, even the single landstand are totally different, like say fair value are totally. I mean, how do you extend to the wider area or different?
Yes.
Yeah.
So thank you for your question. It's a really nice question. So here we are looking at the regional scale problem. And what we assume is for each slope unit, let's say it's mountain face, the geotechnical parameters are tentatively similar, which is a very crude, let's say, assumption. But this is because it's still okay because we are looking at a regional scale problem. But if we want to look more into detail and build a real near real-time or early warning system, then we need to have much more detailed information. But this is at least gives us an idea what's going on, but it's not a conclusive answer. So there is a lot of limitations on it. Yeah, thank you.
So, okay. Thank you very much, Mr. Ashok. It was a very nice presentation. Thank you. Our next speaker is Anand Dong on the topics domain adaptive and efficient neural network for accelerated post-earthquake landslide recognition. You have 15 minutes. 12 minutes, we'll get a ring bell.
Okay, thank you. Thank you to the conference committee and the host. Good afternoon, everyone. My name is Anand Dong from CUG. Under my supervisor, Professor Do. Today, my report title is Domain Adaptive and Efficient Neural Network for Accelerated Post-Earthquake Landslide Recognition. First, I introduce Virat's background. In recent years, frequent earthquake disasters have caused numerous casualties and significant economic losses, often triggering various geological hazards. Earthquakes with magnitude greater than 5 usually trigger landslides, posing a direct or indirect threat to the surrounding environment and people's lives and property. China is an earthquake-prone country in the world, and seismic activities are characterized by wide distribution, high intensity, and high frequency. Okay, for example, in 28, Wenchuan earthquake triggered about 50,000 landslides. So rapid identification and mapping of seismic landslides in post-earthquake areas is key to understanding landslide development, distribution, and risk. It's also critical for earthquake emergency rescue and loss assessment. Okay. Second, research status. There are two kinds of seismic landslide identification: manual interpretation and computer-aided interpretation. Manual interpretation is time-consuming and inefficient, where computer-aided interpretation, especially machine learning and deep learning algorithm, prove interpretation efficiency while ensuring accuracy. Compared to traditional machine learning, deep learning can extract high-level features from raw data, reduce the burden of feature engineering, and perform better when deal with complex data environments. Where there are some problems with deep learning methods. First, the problem of manual labeling costs. Deep learning requires big data support, but usually we don't have. Second, the problem of model generalization. Multi-source landslide images vary greatly in resolution and region, and current models like generalization. Okay. It's back. Okay, and another problem is the speed of model training. Current mainstream computer vision models have high time costs, which conflicts with the timeliness required for disaster emergencies. So, third is study area. The target domain are Hokkaido landslide area in Japan and Luding landslide area in China. September 6, 2018, Hokkaido earthquake, and September 5, 2022, Luding earthquake, they all triggered many landslides. There are geological map of Hokkaido landslide area and Luding landslide area. This is source domain, BG landslide site. The BG landslide site have 770 landslide samples with a resolution of 0.8 meter. So this is the data processing force. We employed 3 meter resolution planet satellite image for Hokkaido and 9 centimeter resolution draw DOM for the Luding earthquake area. The subsequent site production involves 4 key parts. First, landslide boundary delineation and data cropping, label annotation, landslide site establishment. Fourth is the method. This is a technical process to solve the above problem. In deep learning, first we propose a model called multi-scale feature fusion network convolutional neural network as MFFLNet. It achieves a high degree of universality and approves training speed while ensuring accuracy. Second, a deep transfer learning strategy is adopted, which enables MFFLNet to acquire landslide prior knowledge from the source domain and process the training data of the target domain using an improved data enhancement algorithm to reduce overfitting problems. Third, the method was applied to two seismic landslide scenarios in Hokkaido, Japan, and Luding, China. we constructed the MFFL net. First, we modify sigmoid activation function to its sigmoid activation function in this figure. It can improve calculation speed. So we also introduced the ACC channel attention mechanism to replace SE attention mechanism to reduce parameters, and we used the inverted visual structure. Finally, the input mobile net V3 backbone is constructed. It is the backbone of the FFL net. This is advanced training techniques. We introduce optimized learning rate. Warm up chose to use a smaller learning rate at the beginning of training. Train some steps or epochs, and then modify the training for preset learning. And we introduce optimized loss function. That loss can elevate the imbalance between foreground and background. Focus loss makes the model focus more on difficult samples during training. This is deep transfer learning. Deep transfer learning is the source domain pre-trained network, including its network structure and weight parameters, is used to transfer it into deep neural network used by the target domain. And the input data enhancement algorithm, the algorithm of random scanning and random clipping is developed so that the same landslide can be used as the training sample in different resolutions and different angles and presence. These are evolution metrics. Okay, this environmental results. This is introduction of experimental environment. Experiment A, comparing the performance of the deep learning model and the transfer learning model. 10% of the target domain data is selected as the original training samples, and the improved data enhancement algorithm is used to expand the sample and label. The results of experimental A with limited training samples. Transfer learning models generally achieve higher test set accuracy than deep learning models. With the progress of data enhancement, the accuracy of the transfer learning model is gradually improved, and the threshold for achieving the best effect is 60%. Okay, the figure below shows the curve of the loss function. Use the deep learning model and the transfer learning model. The results show that the transfer learning model converges faster, indicating that the model is trained more stably and quickly. This is experiment B, comparing the performance of different models after transfer learning. We compared mainstream semantic segmentation algorithms, FSIN, Deep Level V3, which unit, REST unit, and the MFFL net constructed by myself. That's of experiment B. In the revolution Hokkaido, next lesson is MFL net performs well, though accuracy metrics are slightly lower than VG unit and REST unit, but it has very few parameters and much shorter train time. Okay, in high resolution loading net slide since MFFL net remains stable. These are net slide recognizing result maps, Hokkaido and Luding. Okay, finally, conclusion. Okay, proposed MFLnet lightweight network incorporating multi-scale feature fusion, joint dice, and focal loss, and linear rate warm-up to ensure stronger generalization and probability. Optimized strategy achieved high efficiency and processes through deep transfer learning and advanced data augmentation techniques. Okay, well data performance demonstrated excellent robustness and comprehensive performance in identifying cosmic analysis across various scenarios. These feature prospects of nanoscale intelligence recognition challenge the complexity of the internal structure of deep learning models, the high dimensionality of data processing and the black box nature of prediction models. Technology outlook, explainable machine learning, copying driver of physical model and data model. Visualize the results of different network layers to increase the incredibility of deep learning. And this technical framework of space, air, ground, deep, multi-field integrated net-side disaster observation. The deep integration of AI and big data and geological disaster monitoring and early warning provides new ideas for disaster reduction and prevention. Okay, this is okay.
Thank you very much.
Okay, thank you.
Thank you very much. I think we don't really have time for questions because we'll be too late for lunch. You can ask him any questions if you have now or during the lunch. So the next presenter is Zhui Ming Chan, and in the topic of an agentic machine learning pipeline for drift-away debris flow detection.
Hello everyone, I'm Amin, and today I will talk about agentic machine learning pipeline for drift-aware debris flow detection. So yesterday I already talked how I use agentic AI to help scientists to generate more research ideas. And today I will share some experience how I use agentic AI to take over part of the research. And you might have a question, what is agentic AI? So in 2022, we entered to the year called the AI agent. So the AI agent, just like when you use a GPT, and the agent just handle one task, one input and one output. So let's call the AI agent. But in this year, we entered to the year called the agentic AI. So the agentic AI, it can handle the multiple tasks at the same time. You can assign a parallel algorithm or a sequential parallelism. For example, if you want to build a machine learning model, an agent can do online search. The agent can go to the Google Scholar and to find some proper structure to fit your purpose, then give you a structure suggestion. And another agent can take over the mission to give you summary. And the third agent can just help you to write the code. So that is agentic AI. So today I want to share some experience about agentic AI. And my research location is in Uruguay, and this is a nature debris flow classroom in the world. And we use Sesame signal to do the analysis. So the raw data contain the 70 Sesame features, and the label only 2, debris flow or not debris flow. So the 70 features design debris flow, not debris flow, and each row is 1 minute. And we use the data from 2017 to 2020. But we faced two very, very important problems for the debris flow monitoring. So the first one is concept drift, because environment always change. So how can you build a time generation model to predict the future data? This is really important, because you need to show the evidence how you overcome the concept drift issue. And the second key point is that the data set is extremely imbalanced, because debris flow is not a usual case. Maybe 1 month, just like 1 day or 2 days, or just a couple of hours. So during the normal time, it's just ambient noise. So the no debris flow label is extremely higher than the debris flow label. So in the yield guidance case, the ratio is 340 to 1. Yeah, this is just a video I already showed you yesterday. The debris flow always change the river topography, so you influence your seismic signal. So why some like extinct solution fail? Because like we train the data set on the, we train past data set to predict the future. So the time drift is one important issue. And the second one is that sometimes we might ask a student to build a model, but the student will get his degree. So when you get a degree, then the data set might be assigned to the following students. So the experience cannot be conveyed. And the second, if you train a robust model, how can you have confidence this is robust or not? How many data, how many model structure did you survey? Yeah, this is also a key point. Yeah, when you ask someone he used machine learning, then you might ask a question why you use this model structure. And sometimes they always answer you, yeah, because the structure worked well. Yeah, the prediction result is fit my quality. Yeah, so sometimes there's no logic. And the third one is that if you just use one data set to like 10 different scientists, you might get 11 results. Different scientists have a different thinking, different algorithm to handle their data. So how can we do that? I use a new technology called SDD, spec-driven develop. It's super new. It's just like getting popular in the 3 months. And the structure is announced by the computer science societies. And the SDD is quite simple. It's no code environment. You just need to clearly to understand what you really want to do for your analysis. That's all. So the upper layer is the constitution. Constitution just like a law. You need to ask all AI follow your law to do your analysis. For the yield guidance example, the law is that the training data set is 2017 to 2018. The validation data is 2019. The testing data is 2022. That's the law. AI need to follow it. If you don't write the law if you don't write this rule in the constitution, AI may have the hallucinations because of the probability model. So when you set the law, you will go to the specification. It's your user story. So the user story just write like, I have 70 features. I want to have predict 2 label. One is debris flow and the other one is non-debris flow. Then I want to use machine learning model, or you want to use deep learning model. It's just like a natural language for the specification. So the AI will help you to generate the plan, then give you a task, then you just run it, then just wait the answer. So that's the new year of agentic AI, how to use agentic AI to do your research. So what's the role of the scientist? The scientists need to put your attention to check the task is fit your algorithm or not. Because AI is super diverse, you can have AI to have more creativities. So the role of scientists just narrow the algorithm to fit your thinking. So just two examples, I just asked AI, hey, do your creativity. I don't care about what kind of structure you want to use. I give you 1 hour. Try your best to give you the high performance result. So on your left-hand side, the AI just used the 490 features to train the model, and the F1 score is 0.77. After that, I asked AI to write a report. Then I did not control AI. I just asked AI, revise it. It's not high performance model structure. Think your way to revise your model. So I give it another an hour to ask AI to build a new model structure. So on your right-hand side, the AI decreased the Sesame feature to 78. And the F1 score is extremely increased to 0.84. So the both structure are just based on XGBoost. So I asked the following question, why you use XGBoost? And the AI is super funny. He replied me a lot, because you just give me a 1 hour. I need to get an efficient model to fit your score. And I go back to write a constitution. I need to at least one deep learning model. So we reset the test again. So I attempt the 1 day explorations. So for the initial stage, the AI explored 1,790 experiments, and it's fully automatic. You just set down all structures, then just press enter, then you can go to the gym to have the coffee, then when you come back, everything is done. And the chart show like everyone's goal distribution map. And also the AI know how to improve the recall. Yeah, this is the improvement structure. Is boost the recall at a 0 precision cost. Although the precision is still low, but AI know how to do that. Then you can involve your algorithm or experience to AI, how to do that. This is another exploration from AI. At the first stage, AI failed because my destination is I hope the recall and the precision should be larger than 0.9. So for the initial stage, AI failed the task. So the AI go to the second exploration. And the AI focus on the hard negative mining. Hard negative mining is that the AI put more attention to the false prediction data. So after AI do that, you can see the recall is increased. But in the end, the test still failed. I must say, because it did not fit my destination, recall and precision larger than 0.9. But this is one of the future, how we interact with agentic AI. You can use your logic. Now I just let the AI do whatever he want to do. I did not control AI. Let AI to decide how he want to do the research. But you can use your algorithm to guide AI, which direction, which destination you want to go. So this is another like overall performance and gap analysis. Yeah, my destination is 0.9. So there's still some gap from the AI's result. But this is just very, very basic exploration. I just use 1 day and let AI do he want. So for the final, I just want to emphasize that in this year, we already go to the agentic AI. So how to work with AI is a really important part because we need to guide AI. We need to use our algorithm and our experience then to guide the AI's directions. So we can outsource like a little bit labor issue to the AI. And the key component is that we we cannot outsource of our thinking to AI. You need to have your knowledge base to judge the answer of the AI. This is really important. Yeah. So this is a new working type. The human-machine interaction is one of the very big future. Thank you.
Hello? Yes, thank you very much. Do we have a burning question, very quick one? No?
Hello again. Sometimes I work with electronic engineers, and they are very quick to pick up those things. And engineering geologists, from what I see, we are slow. How can we learn faster and be more confident with this AI?
Okay, so you can give me a workshop. I can give you a very short course on how to use agentic AI. Because I think the concept of using AI is much, much more important than the AI tool. Yeah, how to use the right concept. Because the scientist should be a moral. You know, we need to honest to our data set. But when you control the AI, or when you cannot control AI, it's immoral. Yeah, it will destroy the society in the future. So the concept is also very, very important. Yeah.
Thank you very much. So thank you for your very cool presentation. The next talk is by Muhammad Mahdi Hassan on assessment of hydrogeochemistry and groundwater quality for drinking and irrigation in coastal aquifer on Lakshmipur, Bangladesh using fuzzy overlay. You have 15 minutes and the bell will ring before 2 minutes, like before 2 minutes prior to the end.
Hello everyone. My respected convener, coordinators and researcher, welcome to my presentation. I am MD Mahdi Hassan from University of Rajshahi, Department of Geology and Mining. I am very pleased to have had the opportunity to present my research project, which titled on assessment of hydrogeochemistry and groundwater quality for drinking and irrigation purposes in coastal aquifer of Lakshmipur district, Bangladesh, using fuzzy overlay. These presentations actually consist of 6 chapters. First one is introduction. Groundwater is an essential natural resource that maintain industrial operation, agriculture and human consumption, particularly in areas without access to the surface water. There are 3 common types of groundwater hazard found in Bangladesh. First one is water scarcity. Actually, water scarcity in Bangladesh mainly suffer the northern and northeastern parts of Bangladesh. And the second one is salinity issues. Maximum southern regions are mainly face the salinity issues, and the rest of the areas falls under the arsenic problems. The main objectives of this research project are to determine the physicochemical properties of the groundwater and to assess the groundwater quality for drinking purposes using fuzzy overlay and water quality index. And the last one is to assess the suitability of groundwater for irrigation. The study area. This is the location map of this study area, where the region is bounded by the Ramganj to the north, Kamalnagar and Ramghati to the south, and Roypur to the west, and the Meghna River to the southwest region. In this research, we used 3 softwares to analyze the hydrogeochemical process and water quality index calculations. These are Origin Pro, ArcGIS, and Microsoft Office. In total, 20 groundwater samples were gathered from Bangladesh Water Development Board across the 5 upajelas of the Lakhipur districts. This is the flowcharts of the research work. Primarily focuses on the data collection, and secondary data were taken from the Bangladesh Water Development Board, as we said before, and the physical and chemical parameters are used to calculate the water quality index for both for drinking and irrigation purposes. Similarly, inverse distance weighting of each physical and chemical parameters were identified, and we applied fuzzy membership to normalize each physical and chemical parameters, followed by the fuzzy overlay analysis, and mainly focuses on the fuzzy and overlay. And finally, we generate the groundwater quality index mapping. On the other hand, hydrogeochemical analysis were done by 3 diagrams. First one is Piper diagram, second one is Durov diagram, and the third one is Gibbs diagram. Water quality index. Actually, water quality index is an effective method to provide the exact comprehensive information overall quality of water for human consumption drinking uses. The required formula and the standard tables are here given below. 6 parameters are used to determine the irrigation water quality index. These are sodium percentage, sodium's absorption ratio, residual sodium carbonate, magnesium hazard, Kelly's ratio, and permeability index. These are the 7 physical parameters which are used in this research project, which is pH, temperature, EC, TDS, turbidity, DO, and salinity. These tables represents the 19 chemical parameters results of 20 groundwater samples. These are the spatial distribution map of each chemical parameters. These tables indicates that many samples exceeded the WHO and DOE standard, where calcium, magnesium, sodium, and potassium levels exceeded both WHO and DOE limit, and arsenic and iron concentrations are far above permissible limit, exceeding in all 16 samples. And last, chlorides and salinity values are slightly above to the standard limit in some areas. For calculating water quality index, if the water quality values are high, then it's confirmed the water quality is very poor. In these tables, water quality across most of the sample locations is unsuitable for use, with only minimal area showing acceptable quality. These tables represents that the sodium absorption ratio mostly within the safe range, and majority of residual sodium carbonate values are safe, and permeability index suggests moderate to good water quality for suitable for irrigation. Several samples exceeded the safe magnesium absorption ratio and Kelly's ratio, indicate possible magnesium and sodium dominance risk. And the last one is most water samples are moderately suitable for irrigations and requiring careful management. A fuzzy GIS-based groundwater quality index mapping is done by the fuzzy and overlay method, where each technique's fuzzy linear memberships are taken by the spatial distribution map of each chemical and physical parameters. These are the fuzzy membership map of each parameters, physicals and chemical parameters. And finally, we generate the fuzzy overlay-based groundwater quality index mapping that represents the spatial variation in water quality across the different upajelas of the Lakhipur districts. And the water quality map generated using fuzzy overlay method classified the regions into the 5 categories. And finally, the map shows the Roypur and Ramgati have very poor water quality, where Lakhipur, Sodor, and surroundings areas exhibit high to very high quality, indicating spatial variations in water conditions across the districts. For graphical representations of chemical analysis, Piper, Durov's, and Gibbs diagrams are worked together as an essential tool for hydrogeochemical analysis to know the groundwater chemistry. First one is pipette diagram. Pipette diagram are generally used to classify the water types. In these figures, the most of the sample clustered in the sodium, potassium, chloride, and sulfate dominant zone, indicating a saline or marine influence water types. And the second one is Durov diagram. Durov diagrams are generally used for hydrogeochemical or generally used to reveal the hydrogeochemical process, where most of the sample plots towards the sodium, potassium, and chloride dominant zone, indicating saline water influence. And the last one is Gibbs diagrams. Gibbs diagrams are generally show the hydrogeochemical evolution. In both plots, most groundwater sample clusters within the rock dominance fields, indicating the rock-water interactions. And last chapter is conclusions. As stated in the objectives, some groundwater samples exceeded the permissible limit for parameters such arsenic, TDS, total dissolved solid, salinity, and certain heavy minerals. The result of water quality index and fuzzy overlay map indicate that a significant portion of groundwater in Lokhipur districts falls under unsuitable for drinking purposes, particularly due to the high salinity, TDS, and other chemical contamination. The irrigation water quality index, including sodium percentage, sodium absorption ratio, residual sodium carbonate, magnesium hazard, Kelly's ratio, and permeability index, shows varying suitability across the districts. Thus, we can say that the findings highlights the urgent need for continuous monitoring, appropriate treatment, and sustainable groundwater management practices to ensure the safe water for drinking and irrigations. This is the reference sections where all the sources are given. Thank you for your attention.
Thank you for your quite nice presentation. Do we have any questions? I think we don't really have a lot of time, so if any burning questions, one? No? Okay, thank you. So let's move on. Move on to the new presentation by Kei Singh, if I pronounce it correctly. His presentation is on dynamic landslide susceptibility mapping using INSAR and machine learning fusion. So, yeah, floor is yours.
Okay, thank you. Good afternoon, everyone. Thank you to the organization committee and the host. My name is Ke Xing from China University of Geosciences. Today, my supervisor is Professor Jie Du. Today, I'd like to talk about interpretable multi-orbit INSAR and explainable machine learning for dynamic assessment of optimal landslide areas in radar regions. This my supervisor had introduced. So this is about 3 aspects. 1, AI-based identification. 2, AI-based multi-scale geohazard risk assessment. 3, space, air, ground, deep, or underground, international of things monitoring digital twin vertical large model. So let's begin with the background. As well known, landslides are among the most sudden, frequent, and extremely destructive and dangerous natural disasters worldwide. Especially in the mountainous areas of southwest China, landslides are easily tracked by disturbance from major water conservation projects. It's urgent to carry out research on landslide disaster investigation in reserve areas and dynamic evaluation of landslide susceptibility. Landslide susceptibility mapping has been widely used in spatial probability prediction. In recent years, machine learning-based landslide susceptibility research has become a hot topic in the field of earth science, with its incidence rate gradually increasing each year. New algorithm and models are constantly being proposed and applied, mainly including qualitative and quantitative. Quantitative models are primarily heuristics and rely on expert experience, while quantitative models include both statistic and artificial intelligence models. Among these, artificial intelligence models are more objective and efficient. Besides a superior model, the selection of samples is also crucial, as it can directly affect the accuracy and reliability of the prediction results. This mainly includes geospatial sampling and future space sampling. Meanwhile, more source remote sensing had been widely used in geological disaster monitoring, forming an integrated space, air, ground monitoring technology system. Among them, the process of landslide stability based on INSA is mainly divided into 6 categories, including landslide inventories, joint training, wet overlay, wet coefficients, threshold model, and modification models. Against this backdrop, we conduct research on positive and negative sample imbalance, INSA temporal discontinuity, and the black box problem of the model. So our study area was the Slank Baihetan Reservoir, because the terrain here is complex. We conduct field surveys and ratification work in the study area. We find multiple cracks and bank collapse were discovered, along with heavy fractures, breakages, and subsidence. Meanwhile, the less origin mainly exposed quaternary alluvial deposit and metamorphic sandstone. The table summarizes the detailed data sources. Third, most. The overall technology process includes data preparation and processing, model building and optimization, dynamic evaluation and validation, and finally deformation characteristic and interpretive analysis. This first month is about using INSA technology to obtain surface deformation rate. Second, optimizing negative samples using INSA and IAM models. Third is three tree-based machine learning models will construct decision tree, random forest, and gradient boosting decision tree. The model prediction results are evaluated using AUC values and confusion matrix. Potential landslide area were identified using 2 months, 3-shot model and contingency matrix, and preparative analysis was conducted. Meanwhile, the SHIP algorithm is used to interpret the model's prediction results. The four is about using the above months. The following results were obtained. By comparing the 2 tests of collinearity and correlation, all 12 select catastrophic factors can be used for subsequent model training. All 6 models produce broadly similar spatial patterns. High and very high susceptibility zones are primarily concentrated along the Jinsha River within steep and deeply incised valley and in areas of hot road network density. The RFIY model delivered the highest spatial probability in high-risk zones, underscoring the advantage of IM-based sampling strategy for optimizing in the training data. RC analysis indicates that all 6 models achieved AUC values between 0.7 and 0.9, reflecting moderate to good predictive performance. IF models constantly outperforming the others. IF INSA attained an AUC of 0.814, while IF IOM achieved the highest overall value of 0.866. Models incorporating the IOM both native sampling approach demonstrated notably improved predictive performance compared to those based on the INSA sampling strategy. Our optimized results for potential landslide areas show that threshold model constantly produced substantially smaller potential landslide areas than the contingency matrix. To further evaluate the effectiveness of the contingency matrix, its results were compared against those originating from susceptibility zone and INSA-driven surface deformation rates applied independently. Case 1, high susceptibility, low deformation. Case 2, low susceptibility, high deformation. Case 3, high susceptibility, high deformation. Loss and two-dimensional decomposition results show that from minus 132 millimeter per year to 41 millimeter per year for the ascending orbit, and from minus 8 to 31 millimeters per year for the descending orbit. Vertical deformation results ranged from minus 93 to 29 millimeters per year, and horizontal from minus 55 to 102. Others is crucial to differentiate between movement caused by slope instability and that caused by home activity. Several high deformation areas were attributed to the anthropogenic activities. Among the deformation provinces, I chose some points. Points 1, Xiaomidi landslides and 19 Wanliang Tunnel landslides are confirmed landslides from the validation dataset. Felt vegetations and UV photo further confirmed these stronger deformation zones, revealing geomorphic features such as gullies and surface cracks consistent with ongoing deformation. In the decomposite deformation results, 23 hazard prime points were identified in the vertical component and 18 in the horizontal component. The maximum deformation zones at all 3 Cs occurred at approximately 835 meters elevation, strongly suggesting that instability is primarily driven by fluctuations and in the reservoir water level. In the discussion section, the SHIP framework provided a transparent interpretation of the IF model, quantitatively how each contingent factor influenced landslide susceptibility. The ranking to mean absolute SHIP values reveal a clear dominance of distance to river, followed by slope, less orange aspect, and distance to faults. As well, felt investigation validates these patterns. Single factor shape dependence plots show that susceptibility increased sharply within 500 meters of river, peaks at slope angles between 15 degrees and 35 degrees, and is elevated in moderate elevation bands, where less orange is weak and rainfall more intense. biodiversity plus review synergetic effects. This finding collective confirm that the SHIP framework not only quantifies future importance, but also includes its multi-factor coupling mechanism, providing a physical interpretable foundation for further modeling. Comparative experiments demonstrated that both model performance and interpretability are sensitive to the native sampling strategy. In contrast, the RFIL model achieved the most balanced performance, 86.6% and 71.4%, by effectively leveraging ensemble diversity and refined native sampling. Integrating the susceptibility mapping with insert information via the contingency matrix fusion significantly enhanced landslide delineation, expanding correctly identified areas fourfold relative to the threshold model. Nevertheless, 2 main limits persist: omission the small-scale fusion and incomplete spatial delineation. Finally, let's look at the conclusion and outlook. There are 4 main conclusions: enhanced predictive reliability, improved hazard delineation is solved function, and validation of two-dimension deformation, and mechanism take interpretability of susceptibility drivers. And 3 limitations and future prospect. In conclusion, I hope I have demonstrated the effectiveness of our proposed approach. Last is our team group. And in conclusion, I hope I thank you all very much and for time attention.
Thank you very much, Kixing. We don't really have a lot of time for questions, so let's move on to Professor Ji Do on assessing the impact of multi-resolution DEMS and sampling strategy, uncertainty on deep learning-based debris flow susceptibility mapping. And you have 15 minutes, so, and we'll ring a bell in 13 minutes, right? Yeah.
Hi, Aaron. Because this is my foreign PhD student work, so he did not come, so I replaced him to give a talk. So I also supervise him. He is from Pakistan. Today we will talk about how, the DM, the resolution, and the sampling strategy, how uncertainty in the deep learning based on the debris flow, the sampling mapping. So we consider the topographic effect and the sampling the strategies, how to further, the debris flow, sampling mapping. So we have done the 5 sections. First, introduction, as you may know, and Pakistan also the ranks very high and the pro area. The 18th around the 200 countries for the disaster risk, and making is one of the most the landslide pro area globally. And from this figure, we do the statistical based on the previous and the database. So from this figure, we can see, and the data show on the global, and the debris flow, so the mapping by the country and the mountain range. So from we get to China, take over 0.5% of the research, followed by the Italy, the USA, and India. And we also do the statistics and from the nature handler in Pakistan, and there are different nature handlers such as the landslide, the debris flow, and the flooding. So we compare the most common the disaster in Pakistan and how they affect the people. So Pakistan, and you may know, and ranks the 18 globally in terms of landslide frequency, with in the north region being the particular vulnerable due to the tectonic activity and a high elevation. So from this figure, we can see and and the landslide or debris flow occur and cause serious damage along the highway. And under the picture shown that the debris flow block and the Koram highway in the North Pakistan, connect China and Pakistan. This is a very important secret road. And we pre-study and in this study, and for the last study, many researchers do this similar work. But in this area, in the North Pakistan, field guides do their research. Also, they use the very traditional methods, such as like the statistical method, like the centimeter or HP, expert knowledge. So, and in our research, we have the three research gap. For the, like first, this study is probably how and the topography, resolution affect our debris flow mapping, sediment mapping. Second, this study performed on certain analysis by the symmetrical increase the sample size. We need to consider how percent of sample to affect other result, like the debris flow and the non-debris flow to the robust and the model accuracy. The third, we also used and try to use the flow R model was used to calculate how debris flow propagation along the watershed and define the resolution. And we also assessment that the resolution of how it depends on the flow to spread to the select the optimum DM or some parameters. We methodology. Here, we divide the three processes. The first, we do data acquisition and preparation. And the second, we do how to screen and model development. The third is we do the debris flow mapping and evaluation and the propagation. So work based on three phases. And here, methodology and how to mapping and the debris flow and the image map. We utilize a heuristic approach to identify debris flow in image map. Totally, we run over 100 debris flow and 73 gully debris flow and 35 debris flow and slope debris flow. Totally, around area is over 200 square kilometers. And further, this figure shows on the debris flow and the non-debris flow, the sample distribution over the different classes, how we select and how we divide different the classes. The method we use the deep learning method. We use 4 different deep learning methods. We use for the traditional and the conventional neural network, saying 1D and saying 2D, and we also use the STM long-term memory system, and we also use the IAEG, like recurrent neural networks. We use the 4 deep learning model. And we also do some performance, the field work. As a geologist, we need to go to the field and try to find some scientific problems. So during the field work, many samples we collected from the accumulation zone, and we also measure the width and the length of the stone, and we like a border in the gully. We measure use different measure the tape and length and width and height. Further, we need to evaluate our result whether it's good. So we need to use some evaluation metrics. So we use some general metrics like accuracy, like the precision, AUC, etc. So the case study. In this study, we look in the high Himalaya, from the Kashmir to the Chalas, the region in North Pakistan, and highly the pro to the debris flow, which the most occurred seasonally. So from this animation, we can see, this area, because the tectonic is very active, and this is located because caused by the India and Euro and the planned collision. And this shows some of the real and the picture, how to debris flow cause the serious damage. And also the follow, we do the data collection and the debris flow, destroyed like such as the building and the bridge. So, I mean, destroying in the different, the section in our study area. So this is very serious. And we also do, here, continuous and debris flow blocks the road from 4 hours to many days during the rain season. Because this is located in the north part of along the China and Pakistan, the Sikh road, so it's very important. And the transport materials have different type of grain combination. And we collect the different data source, the multi-data source. We have then different than like DM data. We have then 6.5, 12.5. We also have 19. We have then original data. We don't just try to resample DM data into different resolution. So we have the original. Our work is different from the other work. And such as the other data, yeah. We multi-source data. And the result, in our case study, we totally prepare certain continuing factors, such as some like the topography or hydrology and the other geology map, etc. So before performing our mapping, so we need to do the validation, which factor are important, very important to or is important to contribute our model. So according to this and the RAG, the continuing feature RAG, so based on the random forest, we can see the rainfall has the highest value. As you may know, the debris flow have the 3 conditions. First is the rainfall. Second is then the deposition. The third is the slope angle. So this outdoor is associated with the real condition. And we also the weak the performance is from the result we can see that in the same 1D, all the models perform based on the 12.5 and this and the original the DM data. So and we also do the different effect of the resolution. So we compare the 6.5 and the 12.5. We also perform the different finer DM balance and the debris flow and distribution and satisfactory in the DM the general the factor, the cost and the resolution amplified and the distribution in certain class. And we also do that because this is the blank box, so we try to use the validation, try to do the sharpening analysis. We use the sharpening algorithm, identify these 6 conditional factors contributing to this and the debris flow accuracy. And we, such as the elevation, stream, dissolving, etc. All the factors are positive to the model. So with the culture, we have the loading standard instead. We also try to use the 2-factor dependency plot, reveal the significant feature, interaction, enhance the comprehensive of their collective impact on the debris flow handled in the study area, and the collapse and the materials and the stream buffer contributing the positivity and disorderly, such as the mesodermic and the sediment contributing the positivity. So overall, the rainfall have a pervasive positive influence and negative on the 440 millimeter per year, and elevation also have then the negative impact and have positive contribution to 2,000 millimeter. From our validation result, we can see we use 4D deep learning. LCM, long-term this memory and deep learning have the high accuracy. Next is following IAEG and the record. So from this we can see all the models have the bit good, the performance good, but LCM have the highest performance. And from this, then the table also we also compare each other, so we can see and the best performance and which one is then the best resolution for the DM. And we also measure and we first below we consider the DM the resolution. next we consider the sampling strategy. Symmetrical sampling into an improved accuracy by around 7 to the over 10 across the different resolution. So I excellent as the 90 meters, while STM perform best overall for the debris flow mapping. So I mean, like the symmetrical sampling reduced like the class and the imbalance, and enhance the model, the generation, condition, and try a high performers get the good accuracy score. And we compare with the different like the which we try to explain not the fine the resolution is good so we how to select and purple DM data for mapping the debris flow. And this figure show and why we try to simulate and how debris flow and the flow along the watershed. This is the water area show than the propagation area of debris flow, and in a different areas such as like the Chilas along the Indus River, the water area show than the how the debris flow propagate. And we also, because the parameters of the simulation, we also affect the result. We try to use different such as the height, x, and the travel angle, and we also give them the optimal parameter how to accurately to simulate the propagation. Okay, almost close my talk. So this is just the conclusion. I mean, we evaluate the 4 different deep learning methods. We also try to consider how the DM the resolution to affect our result, and then also we consider and the sampling strategy and give the proper recommendation. Not mean the high or the fine resolution can give them the good result. So it's better to select the proper the topography data and all strategy data. So we also give them the strategy, which one is better for the regional analysis and how to, give them the, final resolution means you need to pay a lot of for the consuming time, especially for the emergency analysis. So we need to set the proper the demand. Okay, I think I will finish my, okay.
Thank you very much.
Okay, thank you.
Professor Jido, do you have any burning questions? No, thank you. Thank you very much for your kind presentation. The next talk is by Nirmal Kafle on analyzing land use and land cover changes in Bhaktapur district using Landsat data with support vector machine and MLC classification approaches.
Thank you. I will try to finish as soon as possible because you all might be hungry. Right. Good afternoon, everyone. My name is Nirmal Kafle, and I'm from Khopo College of Engineering, Bhaktapur. And I would like to thank the organizing committee of this conference for providing me with this opportunity to present here my small study. Today, I'll be presenting my research work on analyzing land use and land cover changes in Bhaktapur district using Landsat data with SPM and MLC classification approaches. Actually, it's not, it should not be kept in AI theme. I have used GIS for the classification of LULC, whatever. Yeah. The study focuses on understanding how the landscape of Bhaktapur has changed over the time by using remotely sensed imagery. This result helped identify major urban growth patterns, agricultural shifts, and environmental changes in one of the Nepal's most rapidly developing districts. beginning with the introduction, accurate and up-to-date land use and land cover information is crucial for sustainable urban planning, environmental monitoring, and disaster management. However, a rapid expansion of Kathmandu Valley, especially Bhaktapur district, has resulted in intense land conversion, leading to increased urban density and loss of vegetation, agricultural land. Several studies, including Hosberger et al. And Sao et al., highlight the importance of monitoring such urban changes through remote sensing. Hence, this study aims to understand how Bhaktapur has changed over last decade and how effectively two classification methods, support vector machine and maximum likelihood classifier, capture these changes. The objective of my study are to analyze land use land cover changes from 2015 to 2025, compare performance of support vector machine and MLC classifiers, perform transition analysis, and generate gain-loss statistics. My study area lies at Bhaktapur, which is the smallest district of Nepal, and it's a very beautiful district. You can explore Bhaktapur, the Darbar Square, the mountain hill Nagarkot. So you can explore after this conference. It's very beautiful. And it's the smallest one with just 119 kilometers square, located on the eastern edge of Kathmandu Valley. It has an elevation range from 1,331 meter to 2,191 meter, and is surrounded by the Mahabharat Hills. The district has seen intense urbanization in the last decade due to the inward migration, infrastructure expansion, and land conversion. For data and materials, I have used Landsat 8 OLITRIS imagery for two time period, 2015 and 2025 AD. Both images have a spatial resolution of 30 meter and were acquired during the dry season to avoid vegetation loss. And the cloud covers are also very negligible in my study area. I processed all data using ArcGIS 10.4 and Google Earth Pro for validation. I applied two supervised classification approaches. One is support vector machine, which is a machine learning based algorithm good for differentiating spectrally similar classes and perform well with limited training samples. Another one is maximum likelihood classifier, which is a classical statistical method and assumes a normal distribution of classes. Both method was applied and for the 5 LULC classifications, the built-up vegetation, forest, barren, and water bodies. Change detection was performed using post-classification comparison, and accuracy was evaluated using confusion matrix and kappa coefficient following Landis and Coates, 1977. Moving towards the result, my result indicate rapid urban expansion during the study period. Built-up area increased significantly with SBM showing plus 12.36% and MLC with plus 3.59%. This aligns with the previous urban studies conducted by Chetri and Moriwaki in 2017 and Prajapati in 2024. Vegetation cover increased slightly due to community forestry and restoration efforts. Barren land decreases sharply, primarily being converted into new settlements and agricultural land. Forest cover remain largely stable with less than 0.5% net change. The transition matrix highlights barren to vegetation was the highest conversion, where support vector machine shows 12.44 conversion and maximum likelihood classifier shows 22.01% conversion. Similarly, barren to built up is also significant with support vector machine 8.09% and MLC 5.79%. Built up expanded mostly at the expense of vegetation. vegetation conforming ongoing urban extension. Vegetation gained the most area overall, while barren land recorded the highest losses. From the gain and loss analysis, vegetation area shows the highest gain in both models, with SBM showing plus 17.87% and MLC showing plus 26.91%. Similarly, barren area shows the largest losses, with support vector machine showing minus 22.20%, whereas MLC is showing minus 28.59%. Built-up area shows significant expansion, which highlights rapid urban growth and infrastructure development. Forest area remains largely stable. It might be due to some government rules. Overall, both support vector machine and MLC classification reveal consistent landscape transformation. The accuracy assessment analysis shows support vector machine performed better with overall accuracy of 79% and kappa of 0.69, and seems good at separating built-up and barren classes. The MLC performance shows overall accuracy of 73% and kappa 0.60%, which shows confusion among vegetation and barren classes. Both classification achieved a substantial agreement, but support vector machine provided more reliable LLC maps. Moving towards conclusion, this study concludes Bhaktapur experienced major LLC transformation between 2015 and 2025, dominated by urban expansion. Support vector machine outperformed maximum likelihood classifier in classifying landside imagery and distinguishing similar classes. Barren land showed the most dramatic decrease, transitioning to vegetation and built-up area. Forest and water bodies remain largely stable. So this study demonstrates the effectiveness of using remote sensing for monitoring urbanizing landscape, and calls for sustainable land use planning and high-resolution future studies. So I would like to acknowledge USGS Earth Explorer for providing free Landsat data, and my institution, Khopo College of Engineering, for academic support for the study. Thank you, everyone, for your attention.
Thank you, Mr. Narmol, for your nice presentation. As we're running out of time, we will not take any questions. Thank you very much.
Thank you, sir.
Our next speaker, Ms. Lubna Yasmin Khandukar. His title of presentation, Investigation of Landslides and Geoenvironment Analysis in Rangamati and adjoining area of Southeastern Hilly District, Bangladesh. The total time, 15 minutes. At 13 minutes, we'll get a ring bell.
Honorable Convener, coordinators, and respected audiences. Good afternoon. I am Lubna Yasmin Khandukar, Deputy Director, Geological Survey of Bangladesh. Welcome to my presentation, which is entitled Investigation of Landslides and Geoenvironmental Analysis in Rangamati and adjoining areas of Southeastern Hilly District, Bangladesh. Today I am going to talk on the mentioned subject. Next, first of all, the location of the study area. Bangladesh occupies the major part of Bengal Delta. The geology of Bangladesh is related to the upliftment of Himalayas and outbuilding of the deltaic landmass by major river system. The southeastern part of Bangladesh consists of Chittagong, Rangamati, Khagrasuri, Bandarban, and Coxbazar districts, which is the extensive hilly terrain of Bangladesh and is prone to landslide. The study area covers the Chittagong-Rangamati National Highway Road from Rangamati Shodor to Kaukali Upojela. And the investigation is aims for the investigation of landslide, geo-environmental analysis, experimental analysis of slope soils, landslide mitigation measures, and management plan. 40 landslides are selected for this study. We can see the location of the study area. Importance of study. As the population is increasing day by day in the hilly terrain, people are cutting trees without knowing the impact. And as the rainfall increases in the for the low pressure of Bay of Bengal, landslide is increasing in this area. And another reason is this area is faced a devastating landslide in June 2017, where 120 people killed, 32 people injured, and 1,500 houses are damaged and loss of economy. Due to this landslide, the Chittagong-Rangamati road was severely damaged, and at the Manikchuri point, the road was partially damaged, and the Shapchuri point, about 60 meters of the road was collapsed, and temporary structure such as Kacha road was built for the communication, and the road was disconnected from the Chittagong district for about 1 week. So this is very important for this study. And another reason is Rangamati is one of the most tourist spot, and this area is only having the only hydraulic power plant of Bangladesh. Overview of the study area. The geology of Bangladesh, regional geology of Bangladesh consists of clastic sedimentary rocks. Physiographically, the study area is comprised of cliffs, ridges, narrow valleys, mountains. As we can see, as we can see in the picture, the location of the landslide and the tectonic map of Bangladesh. And the stratigraphic unit are alluvium, Dupitila Formation, Tipam Formation, Bokabil Formation, and Bhuban Formation. Most of the landslides are occurred in Tipam Formation and Dupitila Formation, which is characterized by sandstone, siltstone, and less claystone. Excuse me. Next, methodology. We have both done field investigation and laboratory analysis has been done for this study. Google Earth images, clinometer, GPS has been used, geological map of Bangladesh has been used for this study. For field soil samples are collected from the hill main part or the weathering part. The soil samples is mostly sandstone, which is medium to coarse grain, high permeable, high porous, and the bond strength of the soil sample shows that which is vulnerable for the landslide. Here is the location of the landslide location where we taken the samples, and we have collected the rainfall data from the Bangladesh Meteorological Department and a statistical yearbook of 2021. Based on the rainfall data analysis, so we have seen that the maximum rainfall occurred in May to October, minimum rainfall April and December, and no rainfall in November. And the first photograph is showing 9 years rainfall scenario, which is collected from the Bangladesh Meteorological Department. And the diagram is showing the monthly rainfall and temperature of the area. In 2017 landslide, the rainfall was recorded 443 millimeter in a single day, and the rest of the day of the event it was in 180 millimeter. So from this observation we can say that a single rainfall with the extensive intensity or a progressive rainfall with time can cause a landslide hazard. Laboratory investigation was performed in the engineering laboratory of Dhaka University, and we have done 10 samples we have tested, and for analysis and a percentage of the soil samples, so we indicated that the samples are mostly silt stone, and with a high percentage of 44 to 70%. The sandstone is 12 to 30%, and the clay stone is 6 to 22%. And we have measured the moisture content and unit weight both, and direct shear test has been done for the cohesion and internal friction angle. Cohesion value is showing that the average cohesion value is 8.05%, 8.05 kilopascal, ranges from 2 to 24 kilopascal, and the internal friction angle is 31 to 39 degree with an average 36 degree, which means that low cohesion value indicates the landslide hazard prone area of this area, and the internal friction angle is deviated from the actual slope angle, which is also indicate the landslide prone area of that study. Landslide characteristics and causes. Most of the landslides are shallow. Shallow mainly, the materials are mainly debris and earth, and the flow and movement is flow and fall. Here we can see the movement and landslide size, and the picture is showing texture and structural attribute of the rock type of the area. And the other figure is showing the stratigraphic of the slope material. So we can see two type of stratigraphic. One is 2-layer, one is 3-layer of the studies area. When the rainfall inflated into the soil, and due to the high load, the toe of the sandstone is going to fall. We can see in the picture. So these are the this photograph is showing the characteristics of the landslides of the area. So this is showing the movement direction along road, and there is a remnant of the slopes and pore drains system, surface structure, and there is main escarp and minor escarp. Landslide assessment and mapping. Landslide assessment, we have produced landslide inventory map and 10 factor maps for this investigation. The factor maps are elevation, road, rainfall, geology, aspect, NTVI, topographic index, and so on. So finally, with the inventory map, we have incorporating with the factors maps, we have produced a landslide susceptibility map. And here you can see landslide susceptibility map, which is we are grading very low, moderate, and high. About 9% of the area fall on the high, and then moderate, then the low, and very low. These are the factor maps which are shown in the photograph. And these are the susceptibility classes that we have done. The susceptibility classes is showing that 9% of the areas is moderate, high susceptible, about 32% moderate, 41% low, and 18% is very low. After that, we have produced a hazard map incorporating with the rainfall data with millimeter per day collecting from the Giovanni web portal. And the hazard map, it is observed that the temporal data incorporating with the geospatial data enhancing the hazard level at the high susceptible areas. And the hazard map is also characterized very low, low, moderate, and high. Then we have produced a vulnerability map. Here is we consider the road infrastructure population for vulnerability, produce vulnerability map. And here we have considered the road as the main element at risk. And we find that the road is the Chittagong Rangamati National Highway Road is high vulnerable. According to the vulnerability map, 20 meters of the road is categorized as high, and 20 to 40 is categorized moderate, and for more than 40 millimeter is categorized as low vulnerability level. And incorporating with a hazard, susceptibility hazard and vulnerability map, then we have produced a risk map, and the risk map is showing us that the Chittagong Rangamati Highway Road is at high risk situation. These are the findings that I have already mentioned, so I am not going through it. These are the remarkable findings from our study. And landslide mitigation measures. So it is very from our observation, we found that landslide mitigation is very important, and for proper road management, the slope stability is very important. And where the steeper slope, the road and the houses are vulnerable in condition. Another remarkable observation is the weightage of the weight of the thickness of the weathering materials. If the thickness of the weathering materials is high, then it is vulnerable for the landslide occurrence. Then it is necessary to determine the weathering gradation. Well, the last observation is the bedding direction. If the bedding direction is opposite to the road, then the road is safe. But it is towards the road, then mitigation measures should be taken. And this photograph is showing Chittagong Rangamati Highway Road, and it is for proper road safety. So it is necessary to build the concrete retaining wall of the road to prevent landslide. The authorities and government has taken some necessary steps and built a retaining wall, but that is not sufficient. And in conclusion, mostly I can say the seasonal variation of rainfall data, low cohesion, low friction, high permeability and high porosity, and weathering characteristics of the rock type makes the area more vulnerable for landslide, and that's why Chittagong Rangamati road cut section road is at high risk condition. So we recommended approximately 12 recommendation, and I'm not going through it.
Thank you, Lubna. Please make it short. We are really
I
running
am
out of time.
about to finish, just 2 lines left. So we have some limitations of our work. We didn't include the socio-economic survey, and we have investigated only the exposed area. So further study is necessary, and because the geo-environmental condition and maturity condition can be changed with time. Thank you.
Thank you. Thank you, Ms. Liberation Khondokar, for a nice presentation. We cannot take any question now, as we are running out of time. If you have any questions during the lunch break, we'll discuss. Thank you very much.
I would request the convener coordinators to please come on the stage for the certificate distribution.
Please, I'm requesting to come of the dais to take the certificate, Mr. Giodo. Please give a clap. Oh, you have two presentations, Mr. Giodo, once again. Yes, thank you very much. Mr. Anandong. Mr. Juiming Chang. Mr. Juiming Chang. Maybe he's absent. Later we'll deliver this certificate to him. MD Mehdi Hassan, please. Okay, call. Which your co-author? Those are co-author of Mr. Mehdi. You want to take a good photo. Mr. K. Singh. Mr. Nirmala. Mr. Nirmal. Maybe he's absent, busy with other works. Ms. Lubna Yasmin Khandokar.
I would request all the presenters to please come on the stage for a group photo. To the convener and the coordinators. Thank you. Certificate first. Thank you, everyone. Thank you, session chair and the coordinators. The lunch is served out, upstairs in the terrace. Thank you.